In the shadowed corridors of history, where ancient stones whisper secrets and forgotten tools mock our modern arrogance, lies evidence that challenges everything we thought we knew about human civilization. Across the globe, scattered like breadcrumbs from a vanished feast of knowledge, stand monuments and artifacts that defy our understanding, technologies so advanced, so impossibly precise, that modern science struggles to explain how they were created. These are not legends or myths, but tangible mysteries that continue to baffle the world's greatest minds. The impossible becomes reality. In the sterile laboratories of MIT, Harvard, and Oxford, some of the world's most brilliant scientists huddle over ancient artifacts with expressions of bewilderment that would make their predecessors proud. Armed with electron microscopes, spectrometers, and computational models that can simulate the birth of stars, they find themselves humbled by technologies created thousands of years ago by civilizations that supposedly knew nothing of advanced engineering, chemistry, or precision manufacturing. The story begins not in the halls of academia, but in the field, where archaeologists have uncovered evidence so extraordinary that it forces us to reconsider everything we believe about the capabilities of ancient civilizations. These discoveries don't fit neatly into our timeline of human progress. They don't conform to our understanding of technological development. Instead, they stand as monuments to human achievement that modern science, despite all its sophistication, cannot fully explain or replicate. Consider the stone blocks at Pumapunku in Bolivia, cut with such laser-like precision that not even a razor blade can slip between their joints. Examine the Damascus steel blades that could slice through European swords like butter, created using techniques that died with their makers and contained what modern analysis suggests might be carbon nanotubes. Marvel at the 1,600-year-old iron pillar in Delhi that has never rusted, protected by metallurgical secrets that modern materials science is only beginning to understand. These are not isolated curiosities. Across 7 continents, in contexts separated by thousands of years and miles, evidence emerges of technologies that challenge our fundamental assumptions about ancient capabilities. From the self-healing concrete of Roman engineers to the astronomical computers of Greek inventors, from the chemical mastery of Egyptian embalmers to the precision instruments of Bronze Age craftsmen, a pattern emerges that suggests our ancestors possessed knowledge and skills that rivaled, and in some cases exceeded, modern achievements. The mystery deepens when we consider the tools supposedly available to these ancient engineers. How does one achieve millimeter-level precision in stone cutting using copper chisels and stone hammers? How does one create steel with properties that modern metallurgy struggles to replicate? How does one design astronomical instruments that can predict celestial events with accuracy that wasn't matched until the invention of modern computers? The conventional explanation, that these achievements represent the pinnacle of human skill and ingenuity working within the constraints of available technology, grows increasingly inadequate as our analysis becomes more sophisticated. Modern attempts to replicate these ancient achievements often fail spectacularly, despite access to advanced tools and comprehensive scientific knowledge. When contemporary stonemasons attempt to recreate the precision of Pumapunku using traditional tools, they achieve results that pale in comparison to the original. When metallurgists try to recreate true Damascus steel, they manage only approximations that lack the legendary properties of the originals. The scientific community has responded to these mysteries with a mixture of fascination and frustration. Some researchers have dedicated their careers to understanding specific ancient technologies, publishing papers with titles like "The Evidence is Cut in Stone," a compelling argument for lost high technology in ancient Egypt, and uncovering the superior corrosion resistance of iron made via ancient Indian iron-making practice. Others have taken a more skeptical approach, arguing that extraordinary claims require extraordinary evidence and that there must be conventional explanations for these apparent anomalies. Yet, as our analytical capabilities advance, the mysteries only deepen. High-resolution imaging reveals details in ancient artifacts that were invisible to previous generations of researchers. Chemical analysis uncovers compositions and processing techniques that challenge our understanding of ancient capabilities. Computer modeling demonstrates that achieving the precision evident in ancient structures would require knowledge and techniques that supposedly didn't exist for centuries or millennia. The implications of these discoveries extend far beyond academic archaeology. If ancient civilizations possessed advanced technologies, what happened to this knowledge? How was it lost? Were these techniques developed independently by different cultures? Or do they represent evidence of knowledge transfer between ancient civilizations? Most intriguingly, what other capabilities might ancient peoples have possessed that we have yet to discover or understand? The story of these mysterious technologies is also a story about the limitations of modern science. Despite our sophisticated instruments and comprehensive theories, we find ourselves confronted by human achievements that we cannot fully explain. This humbling experience reminds us that the boundaries between possible and impossible are often determined by our assumptions rather than fundamental physical laws. In the pages that follow, we will journey together through the most compelling examples of these ancient technological mysteries. We will explore precision stonework that defies explanation, metallurgical achievements that modern science struggles to replicate, optical instruments that shouldn't have existed, energy systems that challenge our understanding of ancient capabilities, astronomical instruments that rival modern computers, chemical processes that outperform contemporary techniques, and information storage systems that represent sophisticated approaches to data management. Each mystery we examine is supported by solid archaeological evidence and rigorous scientific analysis. These are not speculative theories or fringe hypotheses, but documented anomalies that mainstream science acknowledges even as it struggles to explain them. The research draws from peer-reviewed journals, reports from prestigious institutions, and the work of respected archaeologists, engineers, and materials scientists who have dedicated their careers to understanding these ancient achievements. As we embark on this investigation, we must set aside our preconceptions about ancient capabilities and approach these mysteries with the same sense of wonder that drove our ancestors to create these remarkable technologies in the first place. The evidence suggests that human ingenuity has consistently exceeded expectations throughout history, creating achievements that continue to inspire and challenge us today. The ancient world was not a primitive prelude to modern civilization, but a time of remarkable innovation and achievement. The technologies we will explore represent the pinnacle of human capability, created by civilizations that approach technological challenges with different methods but equal intelligence to our own. Their achievements remind us that the story of human progress is not a simple linear progression, but a complex tapestry of knowledge gained, lost, and rediscovered across the millennia. The mysteries we are about to explore will challenge your understanding of ancient capabilities and force you to reconsider the relationship between technological sophistication and historical timeline. They will demonstrate that the boundaries between possible and impossible are often more fluid than we imagine, and that human achievement has consistently exceeded the expectations of each generation. Prepare yourself for a journey into the shadows of history, where ancient stones hold secrets that modern science cannot unlock, where forgotten formulas outperform contemporary chemistry, and where the achievements of our ancestors continue to humble and inspire us. The mysteries we are about to encounter will forever change the way you think about the capabilities of ancient civilizations and the true extent of human potential across the ages. The precision paradox. Stone cutting beyond modern capability. From the laboratories where scientists puzzle over ancient mysteries, we must now journey to the windswept plateaus and ancient quarries where the most confounding evidence lies scattered like pieces of an impossible puzzle. Here, in Bolivia's high-altitude desert, Lebanon's fertile valleys, Peru's mountain fortresses, and Egypt's timeless quarries, stand monuments to precision that modern engineering struggles to comprehend. These are not merely impressive feats of ancient construction. They are technological achievements that seem to mock our contemporary understanding of what should have been possible with Bronze Age tools. The story of ancient precision begins with a simple, devastating observation. The tolerances achieved by ancient stoneworkers often exceed those of modern industrial manufacturing. While our CNC machines boast precision measured in thousandths of an inch, these ancient craftsmen achieved similar accuracy using what archaeologists insist were primitive tools. The implications of this discrepancy ripple through every assumption we make about technological development and human capability. The enigma of Pumapunku, when ancient stones defy physics. High in the Bolivian Andes, where the air is thin and the landscape stretches endlessly toward distant peaks, lies an archaeological site that has transformed from curiosity to scientific controversy. Pumapunku, meaning Door of the Puma in the ancient Aymara language, sits at 12,800 feet above sea level, its massive stone blocks scattered across the Altiplano like the remnants of some titanic construction project abandoned by gods. The blocks themselves tell a story that conventional archaeology struggles to interpret. Crafted from andesite and red sandstone, these monuments to precision were cut with tolerances that would challenge a modern machinist working with the finest equipment. The famous H-shaped blocks, some weighing up to 131 tons, feature surfaces so perfectly flat that they seem to gleam in the harsh mountain sunlight. The joints between stones are so precise that archaeologists report with amazement that not even a razor blade will fit between them. But precision is only the beginning of Pumapunku's mystery. The blocks display complex three-dimensional geometries that would require sophisticated understanding of mathematics and engineering. Perfect 90-degree angles, intricate interlocking systems, and surfaces ground to within millimeter tolerances speak to capabilities that seem impossible for a civilization that supposedly lacked even the wheel. The drilling work is particularly extraordinary. Circular holes with perfectly smooth walls, some intersecting at precise angles that would challenge modern drill operators. Dr. Jean-Pierre Pratzen, a leading expert on ancient Andean construction techniques, has spent decades studying these monuments. His conclusion, published in multiple peer-reviewed journals, is both humbling and mystifying. The techniques used at Pumapunku remain unknown to us at this time. Modern stonemasons who have attempted to replicate this work using traditional tools report extreme difficulty achieving even crude approximations of the original precision. The mystery deepens when we consider the logistics of construction. The andesite blocks were quarried from locations 55 miles away, across terrain that would challenge modern transportation equipment. The red sandstone came from quarries 6 miles distant, yet these massive stones were somehow moved across the Altiplano and positioned with millimeter accuracy. No roads, no wheels, no draft animals. Yet somehow these ancient engineers accomplished what modern project managers would consider nearly impossible even with contemporary equipment. Recent MIT research has demonstrated ingenious methods for moving massive stones using balance and leverage techniques. But these experiments explain only transportation, not the cutting precision that remains the site's most baffling feature. When modern stone carvers attempt to achieve similar results using reconstructed ancient tools, they produce work that pales in comparison to the originals. The precision at Pumapunku appears to be the product of manufacturing techniques that were lost with their creators. Baalbek, engineering the impossible. From the high Andes, our investigation moves to the ancient crossroads of Lebanon, where the mysteries of precision take on even more staggering dimensions. In the Bekaa Valley, where civilizations have risen and fallen like wheat before the harvest, stands Baalbek, a testament to human ambition that pushes the boundaries of believability. The trilithon stones of Baalbek represent perhaps the most audacious engineering project ever attempted by ancient builders. These 3 massive limestone blocks, each weighing approximately 800 tons, were somehow quarried, transported, and lifted into position as part of the temple foundation. To put this achievement in perspective, each block weighs more than a fully loaded Boeing 747, yet they were positioned with such precision that their joints remain perfect after 2 millennia. The engineering challenges multiply when we examine the recently discovered stones that were never moved from their quarries. The stone of the pregnant woman weighs nearly 1,000 tons, while the largest discovered block tips the scales at an estimated 1,650 tons, making it the heaviest stone block ever quarried by human hands. These monoliths lie in the quarry 800 meters from the temple site, their surfaces bearing the tool marks of ancient stoneworkers who possessed ambitions that seem to exceed any reasonable expectation of their capabilities. Modern heavy lifting equipment would struggle with these stones. The largest contemporary cranes can lift approximately 20,000 tons, but they require massive support structures and careful coordination. To move the 1,650-ton stone would require a coordinated effort of multiple cranes working in perfect synchronization, a feat that would challenge even contemporary project managers with unlimited resources and modern communication systems. Yet the ancient builders of Baalbek accomplished something arguably more impressive. They achieved precision placement of these massive stones without modern machinery. The trilithon blocks fit together with joints so tight that centuries of earthquakes have failed to displace them. The surfaces were dressed to tolerances that would impress modern stonemasons, and the overall engineering demonstrates an understanding of structural mechanics that rivals contemporary knowledge. The quarrying techniques themselves present additional puzzles. The stones were extracted from the bedrock using methods that left smooth, precise surfaces. The tool marks visible on the unfinished blocks suggest systematic cutting techniques, yet no tools capable of such precision have been discovered. The largest stone remains partially attached to the bedrock, frozen in the moment of its creation like a snapshot of ancient ambition. Sacsayhuaman, the earthquake-defying masterpiece. Our journey through the world of ancient precision next takes us to the ancient capital of the Inca Empire, where the fortress of Sacsayhuaman overlooks the city of Cusco like a stone guardian frozen in time. Here, the mystery of ancient precision takes on a different character, one that emphasizes not just accuracy, but engineering wisdom that has enabled these structures to survive over 500 years of earthquakes in one of the world's most seismically active regions. The stones of Sacsayhuaman present a puzzle that has confounded engineers for centuries. Unlike the regular blocks we might expect from ancient construction, these stones are shaped like massive three-dimensional puzzles, with complex curves and angles that somehow fit together with extraordinary precision. The largest stones weigh up to 200 tons, yet they were positioned with such accuracy that archaeologists report a single piece of paper will not fit between them. The construction technique appears to violate common sense. How does one create irregularly shaped stones that fit together perfectly with their neighbors? The traditional explanation, that the stones were shaped in place through trial and error, becomes increasingly inadequate when we consider the size and weight of the blocks involved. Moving a 200-ton stone into position for test fitting would require massive effort, making iterative adjustment impractical. Modern structural analysis reveals the genius behind this apparent chaos. The irregular shapes create a flexible structure that can absorb seismic energy without failure. During earthquakes, the stones can move slightly relative to each other, dissipating energy that would crack or collapse conventional masonry. This principle, known as base isolation, has been adopted by modern earthquake-resistant design, yet the Inca achieved it centuries before the scientific principles were understood. The precision required for this system defies conventional understanding of ancient capabilities. Each stone must be shaped to fit perfectly with multiple neighbors while maintaining structural integrity under enormous loads. The mathematics involved would challenge contemporary engineers, yet the ancient builders achieved this precision without modern surveying equipment, computer modeling, or precision measuring tools. Recent attempts to replicate Sacsayhuaman's construction techniques have met with limited success. Experimental archaeologist Vince Lee has demonstrated possible methods for shaping and positioning the stones, but his small-scale experiments cannot match the precision and scale of the original construction. The techniques that created this marvel remain largely mysterious. The drilling enigma, piercing stone with impossible speed. Perhaps nowhere is the mystery of ancient precision more evident than in the drilling work discovered at ancient sites across the world. In Egypt, granite cores extracted from stone blocks provide evidence of drilling capabilities that seem to exceed the supposed limitations of ancient technology. These cores, discovered by archaeologist Flinders Petrie in the 1880s, display characteristics that continue to baffle modern experts. The most extraordinary feature of these granite cores is their feed rate, the speed at which the drill bit cut through the stone. Modern analysis suggests feed rates that are 500 times faster than what contemporary diamond-tip drill bits can achieve when operated by hand. The cores display consistent concentric lines that indicate uniform drilling speed, while the smooth, circular holes suggest the use of tubular drilling implements rotating at high speed. The precision of these ancient drill holes challenges every assumption about Bronze Age capabilities. The holes are perfectly circular with smooth walls, while the extracted cores show no signs of the wandering or irregularities that would be expected from hand-operated tools. The concentric lines visible on the cores suggest not just rotational drilling, but drilling at consistent speed under constant downward pressure. Modern attempts to replicate these results have yielded mixed success. The University of Pennsylvania's recent experiments confirmed that copper tools with abrasive compounds can produce similar concentric lines, but the hand-powered methods cannot achieve the observed feed rates. The actual drilling implements used to create these holes have never been found, leaving only the cores as evidence of capabilities that seem impossible for their time. The implications of this drilling evidence extend far beyond the specific techniques involved. If ancient craftsmen possessed drilling capabilities that rival modern equipment, what other technologies might they have developed? The precision evident in these cores suggests manufacturing capabilities that approach industrial levels, achieved through methods that remain completely mysterious. The mystery deepens when we consider the purpose of this drilling work. Many of the precise holes appear to be functional rather than decorative, suggesting that they were part of larger technological systems whose purpose we can only guess. The precision and consistency of the work implies systematic production methods rather than isolated achievements, hinting at technological capabilities that were far more advanced than conventional archaeology suggests. As we stand before these monuments to ancient precision, we must confront the inadequacy of our explanations. The evidence carved in stone tells a story of capabilities that challenge our understanding of technological development and human achievement. These are not crude approximations or lucky accidents, but demonstrations of systematic precision that modern science struggles to explain. The precision paradox forces us to reconsider fundamental assumptions about ancient civilizations and their capabilities. If our ancestors could achieve such extraordinary precision in stone cutting, what other technologies might they have possessed? The evidence suggests that the boundaries between possible and impossible are far more fluid than we imagine, and that human achievement has consistently exceeded the expectations of each generation. From these monuments of impossible precision, our investigation must now turn to another realm of ancient achievement that challenges modern understanding: the metallurgical mysteries that reveal lost formulations and forgotten techniques that modern science is only beginning to comprehend. The metallurgical enigma, lost formulations of the ancients. From the impossible precision of ancient stonework, we now venture into an even more mystifying realm, one where the very atoms seem to have been commanded by forgotten masters. If the stone monuments we have examined represent triumphs of mechanical precision, the metallurgical achievements of ancient civilizations reveal something far more profound: a mastery of chemistry and materials science that modern laboratories struggle to replicate. Here, in the realm of molten metal and molecular manipulation, we encounter technologies so advanced that their secrets died with their creators, leaving only tantalizing clues in the form of artifacts that continue to baffle the world's most sophisticated analytical instruments. The mystery of ancient metallurgy begins with a fundamental paradox. How did civilizations without modern scientific understanding create materials that often exceeded the performance of contemporary alternatives? The answer lies buried in the molecular structure of ancient metals, in chemical processes that were perfected through generations of trial and refinement, and in knowledge systems that integrated practical experience with theoretical understanding in ways that modern science is only beginning to appreciate. Damascus steel, the nanotechnology of medieval times. In the souks of Damascus, where merchants once displayed blades that could slice through silk scarves or cleave enemy swords in half, began one of history's most enduring technological mysteries. True Damascus steel, forged from what steel ingots imported from the mines of ancient India, possessed properties that seemed to transcend the limitations of medieval metallurgy. These legendary blades combined razor sharpness with extraordinary flexibility, creating weapons that could bend without breaking and hold edges that remained keen through countless battles. The production of Damascus steel reached its zenith between the 11th and 16th centuries, when skilled craftsmen in Syria transformed raw Indian steel into blades that became the stuff of legend. European crusaders spoke with awe of swords that could cut through their own weapons, while Arab poets composed verses celebrating blades that seemed to capture the very essence of fire and water in their watered patterns. Yet by 1750, the technology had vanished as completely as if it had never existed, leaving only the blades themselves as evidence of capabilities that modern metallurgy is still struggling to understand. The distinctive watered patterns that gave Damascus steel its name were not merely decorative. They were the visible manifestation of a complex internal structure that modern science has revealed to be centuries ahead of its time. Dr. John Verhoeven's groundbreaking research at Iowa State University uncovered the secret. The steel's extraordinary properties resulted from carbide banding caused by the microsegregation of trace elements, particularly vanadium, molybdenum, chromium, and manganese. These elements, present in quantities measured in parts per million, created microscopic structures that function like internal scaffolding, giving the steel its legendary combination of hardness and flexibility. But the true revelation came in 2020, when researchers discovered what appeared to be carbon nanotubes embedded within the steel matrix. These microscopic structures, formed from plant fibers used in the ancient smelting process, represent technology that wasn't officially invented until the late 20th century. The discovery suggests that medieval craftsmen had inadvertently created nanotechnology through their traditional methods, achieving at the molecular level what modern materials science accomplishes through precisely controlled laboratory processes. The mystery deepens when we consider the production process itself. The wood steel that provided the raw material came from specific mines in India, but the exact locations and compositions of these or deposits remain unknown. Each blade had a unique composition, suggesting that the steel varied with its source and that craftsmen had to adapt their techniques to work with different materials. The complete traditional process died with its practitioners, leaving modern metallurgists to reverse engineer techniques from the finished products. Contemporary attempts to recreate Damascus steel have achieved only partial success. Dr. Verhoeven's reproductions required adding precise amounts of vanadium to modern steel, while other researchers have used additive manufacturing to create Damascus-like patterns. Yet none of these modern techniques can exactly replicate the traditional process or achieve all the properties of the original blades. The complete understanding of Damascus steel production remains lost, a casualty of the breakdown in knowledge transmission that occurred when traditional craftsmen were displaced by industrial processes. The Delhi Iron Pillar, 16 centuries without rust. In the courtyard of the Qutub Minar in Delhi, where pilgrims and tourists gather daily to marvel at one of India's most enduring mysteries, stands a monument that defies every expectation of ancient metallurgy. The Delhi Iron Pillar, erected during the reign of Chandragupta II between 375 and 415 CE, has stood exposed to the elements for over 1,600 years without showing significant signs of corrosion. While modern iron structures require constant maintenance to prevent rust, this ancient column continues to gleam with the luster of freshly forged metal. The pillar's resistance to corrosion represents a metallurgical achievement that modern materials science has only recently begun to understand. Standing 7.2 meters tall and weighing approximately 6 tons, the column was forged from wrought iron with a composition that seems unremarkable at first glance. Yet hidden within its molecular structure lies a sophisticated anti-corrosion system that rivals modern weathering steel technologies. The secret, revealed through decades of research by Dr. R. Balasubramaniam of the Indian Institute of Technology, lies in the pillar's high phosphorus content, 0.25% compared to the trace amounts found in modern steel. This phosphorus, deliberately incorporated through the ancient smelting process, creates a protective crystalline iron-hydrogen phosphate hydrate layer when exposed to Delhi's alternating wet and dry climate. This protective film, only 1/20th of a millimeter thick, forms a barrier that prevents oxygen from reaching the underlying iron. The ancient Indian smelting process that created this marvel was far more sophisticated than traditional accounts suggest. The ironworkers deliberately selected woods high in phosphorus content, particularly from the Cassia auriculata tree, incorporating these materials into the furnace along with iron ore. The resulting chemical reactions created wrought iron with built-in corrosion resistance, while the forge welding process used to create the pillar's final form distributed protective elements throughout the metal structure. Modern analysis has revealed additional layers of sophistication in the pillar's construction. The metal contains slag particles that enhance cathodic reduction reactions, creating a complex electrochemical system that actively prevents corrosion. The pillar's surface also shows evidence of protective envelopes of oxides and slag that were deliberately incorporated during the forging process, creating multiple layers of protection that work in harmony to preserve the underlying iron. The techniques used to create the Delhi Iron Pillar were not unique to this single monument. Similar corrosion-resistant iron objects have been discovered throughout India, suggesting that this technology was widely understood and systematically applied. The knowledge was passed down through generations of ironworkers who understood through practical experience principles that modern corrosion science has only recently identified. The loss of this technology represents one of history's most significant casualties of industrial progress. When British colonial administrators introduced modern smelting techniques to India in the 19th century, they displaced traditional methods that had been refined over millennia. The ancient knowledge, encoded in the practices of hereditary craftsmen rather than written texts, vanished within a generation as traditional ironworking communities were disrupted by industrial competition. Ancient aluminum, the electrochemical impossibility. Deep within the collections of museums worldwide lie artifacts that challenge one of our most fundamental assumptions about ancient technological capabilities. Scattered reports of ancient aluminum objects, goblets, ornaments, and tools have surfaced from archaeological contexts spanning thousands of years, creating a mystery that strikes at the heart of our understanding of ancient chemistry. The problem is simple yet profound. Aluminum requires electricity for extraction from its ores, and the Hall-Héroult process that makes aluminum production possible wasn't developed until 1886. Yet these artifacts appear to predate this technology by millennia. The mystery of ancient aluminum begins with the metal's unique properties. Unlike iron or copper, which can be smelted from their ores using traditional furnaces, aluminum binds so tightly to oxygen that separating it requires enormous amounts of electrical energy. Before the development of industrial electrolysis, aluminum was more precious than gold, used only for the finest jewelry and ceremonial objects. Napoleon III famously served his most honored guests with aluminum cutlery, while less important visitors made do with mere gold implements. The most intriguing claims of ancient aluminum center on artifacts allegedly discovered in archaeological contexts far predating the Industrial Revolution. The Wedge of Ayad, discovered in Romania in 1974, was initially reported to be an aluminum alloy object found alongside mastodon bones in geological layers dating to 20,000 years ago. Similar reports have emerged from excavations in China, Peru, and other locations, each claiming to represent evidence of ancient aluminum production. However, rigorous scientific analysis has revealed the complex truth behind these claims. The distinction between aluminum compounds and metallic aluminum is crucial to understanding this mystery. Ancient civilizations were indeed familiar with aluminum compounds, particularly alum, aluminum potassium sulfate, which they used for dyeing, tanning, and medicinal purposes since at least the 5th century BCE. These compounds occur naturally and require no advanced technology to extract or refine. The few objects that initially tested positive for metallic aluminum have been systematically re-examined using modern analytical techniques. In most cases, these investigations have revealed more prosaic explanations: modern contamination, naturally occurring aluminum oxides, or misidentified materials. The Wedge of Ayad, for example, was later revealed to be a modern aluminum object that had somehow become incorporated into the archaeological deposit through post-excavation contamination. Yet the persistence of these claims reflects a deeper truth about ancient chemical knowledge. While ancient civilizations may not have possessed the ability to extract pure aluminum, they demonstrated sophisticated understanding of metallurgy and chemistry that often exceeded what we might expect from their technological context. The search for ancient aluminum has led researchers to investigate the full spectrum of ancient chemical achievements, revealing capabilities that challenge our assumptions about the development of materials science. Greek fire, the chemical weapon lost to time. In the harbor of Constantinople, where the great walls of Byzantium once stood against the tide of history, Byzantine ships deployed a weapon so terrifying that enemy fleets would flee at the mere sight of the bronze tubes from which it was projected. Greek fire, the secret weapon of the Byzantine Empire, burned with an intensity that water could not quench, clinging to ships and flesh with the tenacity of liquid death. For over 700 years, from 678 to 1453 CE, this incendiary substance helped preserve the last remnant of the Roman Empire, its formula guarded more closely than the crown jewels themselves. The unique properties of Greek fire made it one of history's most effective weapons. Unlike ordinary fire, it burned vigorously on water, possibly becoming even more intense when wet. It adhered to whatever it touched, creating a napalm-like effect that could not be extinguished by conventional means. Contemporary accounts describe the substance as flowing like liquid, burning like oil, and consuming everything in its path with an appetite that seemed supernatural. The tactical applications of Greek fire were as varied as they were devastating. Naval forces used it to destroy enemy fleets, projecting the burning liquid through bronze siphons that functioned like ancient flamethrowers. Land forces employed it in siege warfare, creating barriers of flame that could halt enemy advances. The psychological impact was perhaps even more significant than its physical effects. The mere threat of Greek fire could cause enemy forces to abandon their positions rather than face the horrible death it promised. The secrecy surrounding Greek fire's production was absolute. The Byzantine emperors decreed that revealing the formula was punishable by death, and the manufacturing process was compartmentalized so that no single person knew the complete recipe. This security system was so effective that even when samples of Greek fire were captured by enemies, they could not be reverse-engineered to reproduce the original formula. Modern theories about Greek fire's composition center on petroleum-based mixtures enhanced with various chemical additives. The most widely accepted theory suggests a combination of petroleum oil, pine resin, sulfur, quicklime, and possibly potassium nitrate. The quicklime would react violently with water, potentially explaining the substance's ability to burn more intensely when wet. Alternative theories propose calcium phosphide, which would release spontaneously combustible phosphine gas on contact with water. Despite numerous attempts, no modern recreation has successfully matched all the described properties of Greek fire. The missing components likely explain why captured samples could not be reproduced by Byzantine enemies. The complete formula was never written down, existing only in the memories of specialist craftsmen, whose knowledge died with the fall of Constantinople in 1453. The loss of Greek fire represents more than the disappearance of a single technology. It exemplifies the fragility of knowledge systems that depend on oral transmission and hereditary craft specialization. When the Byzantine Empire fell, the entire production network that had maintained this secret for centuries vanished overnight, taking with it not just the formula but the accumulated experience of generations of chemical craftsmen. Optical mysteries. Ancient precision instruments. From the molecular mysteries of ancient metallurgy, where craftsmen commanded atoms with forgotten wisdom, we now enter a realm where light itself was bent to serve human purposes in ways that challenge every assumption about ancient capabilities. If the metallurgical achievements we have examined represent mastery over matter, the optical technologies of ancient civilizations reveal something even more extraordinary: the ability to manipulate light with precision that rivals modern instruments, to create devices that computed the movements of celestial bodies, and to fashion objects with tolerances that would challenge contemporary manufacturing. The story of ancient optics begins not in the laboratories of modern science, but in the workshops of craftsmen who understood through practical experience principles that we now express through complex mathematical equations. These were not accidental discoveries or crude approximations, but systematic applications of optical knowledge that demonstrate scientific understanding centuries ahead of its supposed time. The evidence lies scattered across museum collections worldwide: lenses ground with mathematical precision, instruments that predicted eclipses with uncanny accuracy, and carvings so microscopic that they seem to exceed the capabilities of human vision. The Antikythera mechanism, history's first computer. In the depths of the Mediterranean, where ancient currents have carried the debris of civilizations for millennia, a Greek sponge diver named Elias Stadiatis made a discovery in 1901 that would challenge every assumption about ancient technological capabilities. Exploring a shipwreck off the coast of Antikythera, he surfaced with tales of bronze statues and marble figures scattered across the seafloor like the remnants of some sunken palace. Among these treasures lay a corroded bronze object that would prove to be one of history's most extraordinary technological achievements. The Antikythera mechanism, as it came to be known, represents nothing less than the world's first analog computer. Dating to approximately 150 to 100 BCE, this intricate bronze device contained at least 37 precisely cut gears arranged in a complex system that could predict astronomical positions with remarkable accuracy. The mechanism could calculate the positions of the Sun, Moon, and 5 known planets, predict lunar phases and eclipses, and display the 18.6-year Saros cycle that governs eclipse patterns with a precision that would not be matched for over 1,000 years. The complexity of the Antikythera mechanism defies every expectation of ancient capabilities. The gear teeth were cut to millimeter precision in bronze, requiring advanced metallurgical knowledge and mechanical engineering skills that seem impossible for the Hellenistic period. The device incorporated sophisticated planetary period relations. Venus tracked over 462 years, Saturn over 442 years, with shared gear systems that demonstrate computational efficiency rivaling modern engineering principles. Recent breakthrough research published in 2021 by University College London provided a complete reconstruction of the mechanism's front display, revealing layers of sophistication that continue to astonish researchers. The study uncovered evidence of advanced mathematical understanding, including the use of Babylonian astronomical data combined with Greek theoretical knowledge to create a hybrid system that optimized both accuracy and mechanical efficiency. Perhaps most remarkably, a 2024 University of Glasgow study using gravitational wave detection techniques discovered that the mechanism's calendar ring contained 354 to 355 holes positioned with extraordinary precision, 0.028 millimeters accuracy. This level of precision exceeds what should have been possible with ancient tools, suggesting manufacturing techniques that approach modern industrial standards. The gearing system itself represents a masterpiece of ancient engineering. The main gear ratios were calculated to match the complex periodicities of planetary motion, requiring mathematical understanding that would not be formally developed until the work of Kepler and Newton. The mechanism's designers somehow managed to encode astronomical knowledge spanning centuries of observation into a mechanical device that could perform calculations with the turn of a handle. The precision required for the Antikythera mechanism's construction challenges our understanding of ancient manufacturing capabilities. Modern attempts to recreate the device using period-appropriate tools have met with limited success, achieving only crude approximations of the original's precision. The bronze gears show no signs of the irregularities that would be expected from hand-cutting, suggesting systematic production methods that remain mysterious. Crystal skulls, the precision paradox. In the shadowed halls of museums and private collections, where ancient artifacts whisper secrets of forgotten civilizations, crystal skulls have captured imaginations for over a century. These translucent monuments to human artistry, carved from single blocks of clear quartz, were long celebrated as examples of ancient precision that modern technology could barely match. The most famous examples, including the Mitchell Hedges skull and the British Museum skull, were said to demonstrate carving techniques that would have required centuries of painstaking work using only primitive tools. The mystery of crystal skulls lies not just in their beauty, but in the apparent impossibility of their creation. Quartz crystal, ranking 7 on the Mohs hardness scale, presents extraordinary challenges for carving. The material's brittleness means that any significant impact or irregular pressure can cause catastrophic fractures, while its hardness requires tools that ancient civilizations supposedly did not possess. The precision evident in the finest examples, smooth surfaces, detailed anatomical features, and optical properties that create mysterious light effects, seem to represent the pinnacle of ancient craftsmanship. Early analysis of crystal skulls fueled speculation about advanced ancient technologies. The Mitchell Hedges skull, discovered in Belize in the 1920s, was subjected to extensive examination at Hewlett-Packard's Crystal Technology Laboratory. The researchers reported finding no evidence of modern tool marks, leading to claims that the skull must have been carved using techniques unknown to contemporary science. The skull's optical properties, which create mysterious light phenomena when illuminated, added to its mystique. However, the application of more sophisticated analytical techniques has revealed a different story. Scanning electron microscopy analysis of crystal skulls has consistently shown evidence of high-speed rotary tools with diamond abrasives, technologies that were not available to ancient civilizations. The tool marks visible under magnification display the characteristic patterns of modern manufacturing equipment, while the precision of the carving suggests industrial rather than hand production methods. The scientific consensus that emerged from these investigations is clear. All crystal skulls that have been subjected to rigorous analysis are modern creations. The use of silicon carbide abrasives, a 20th century invention, has been detected in several specimens, while material analysis shows quartz from Brazilian or Madagascan sources rather than the Mesoamerican origins claimed for many skulls. Perhaps most tellingly, no crystal skull has ever been discovered in a documented archaeological excavation. While genuine ancient cultures did create skull carvings from various materials, including jade and obsidian, The large clear quartz skulls that have captured public imagination appear to be products of 19th and 20th century craftsmen working with modern tools. The crystal skull phenomenon illustrates the importance of rigorous scientific analysis in distinguishing between genuine ancient achievements and modern misconceptions. While these objects may not represent ancient technology, they demonstrate the precision that modern tools can achieve when applied to challenging materials, serving as reminders that extraordinary claims require extraordinary evidence. Ancient lenses, seeing the impossible. Far from the crystal skull controversy, genuine ancient optical achievements await discovery in museum collections worldwide. The Nimrud lens, discovered in 1850 at the Assyrian Palace of Nimrud, Iraq, represents sophisticated optical technology that predates European lens development by over 2,700 years. Carved from natural rock crystal, this carefully ground lens demonstrates deliberate optical engineering that challenges assumptions about ancient scientific knowledge. The Nimrud lens exhibits properties that suggest systematic optical understanding rather than accidental achievement. Modern analysis reveals consistent curvature with a focal length of approximately 12 centimeters, equivalent to a 3 times magnifying glass. The precision grinding required to achieve this optical performance would have demanded extraordinary skill and possibly centuries of incremental refinement using only stone tools. Recent analysis by Dr. Ángel Tomás Camacho Garcia suggests the lens may actually be a toroidal lens designed to correct astigmatism, a level of optical sophistication that implies understanding of complex visual principles. The discovery challenges traditional timelines of optical development and suggests that ancient civilizations may have possessed systematic knowledge of light manipulation techniques. Professor Giovanni Pedinato's controversial theory proposes that the lens was part of an ancient telescope system, which would explain the sophisticated astronomical knowledge demonstrated by Assyrian astronomers. While this interpretation remains debated, the precision of the lens itself is undeniable, representing optical engineering that seems impossible for its historical context. The Nimrud lens is not unique. Over 450 ancient optical artifacts have been identified in museums worldwide, most providing magnification levels between 1.5 times and 2 times. The global distribution of these lenses suggests widespread optical knowledge rather than isolated discoveries, implying systematic understanding of optical principles that modern science assumed were unknown to ancient civilizations. The precision achieved in ancient lens production indicates understanding of optical theory that parallels modern knowledge. The consistent curvatures and focal lengths suggest mathematical approaches to optical design, while the quality of the grinding implies systematic production methods that could reliably produce functional optical instruments. Microscopic engravings beyond human vision. Perhaps the most mysterious aspect of ancient optical achievements lies in the realm of microscopic craftsmanship. Engravings and carvings so small and precise that they seem to exceed the capabilities of naked eye vision. Across archaeological contexts spanning millennia, researchers have discovered examples of ultrafine work that challenges our understanding of ancient visual capabilities and suggests the possible use of optical aids that have not survived in the archaeological record. Assyrian cylinder seals provide some of the most compelling examples of microscopic ancient craftsmanship. These small stone cylinders, used to create impressions in clay, contain details that require magnification to fully appreciate. The finest examples display intricate scenes with figures, animals, and cuneiform inscriptions carved in spaces measuring only millimeters across. The precision of these engravings suggests either extraordinary visual acuity or the use of magnifying devices that enable detailed work beyond normal human capabilities. Archaeological evidence from Europe reveals 38,000-year-old engravings that employed Pointillist techniques, creating images through the systematic application of tiny dots. This technique, which would later be employed by artists like Seurat and Liechtenstein, demonstrates sophisticated understanding of visual perception principles that seem remarkably advanced for Paleolithic cultures. The precision required for effective pointillism suggests systematic approaches to image creation that challenge assumptions about early human cognitive capabilities. Modern analysis using electron microscopy has revealed the characteristic patterns of different ancient tool types, allowing researchers to distinguish between handheld implements and more sophisticated equipment. The regularity of some ancient engravings suggests the use of guide systems or mechanical aids that enabled consistent precision across complex surfaces. The jewelry and decorative arts of ancient civilizations often display microscopic details that exceed what would be expected from handheld tools. Ultrafine filigree work, microscopic gemstone settings, and surface textures that create optical effects through precise manipulation of light reflection all suggest manufacturing capabilities that approached modern precision levels. The techniques required for microscopic engraving suggest specialized knowledge systems that were transmitted through master-apprentice relationships over generations. The consistency of quality across different regions and time periods implies systematic training methods that could reliably produce craftsmen capable of extraordinary precision work. The precision manufacturing mystery. The optical achievements of ancient civilizations reveal a pattern of precision manufacturing that challenges our understanding of ancient capabilities. From the complex gearing of the Antikythera mechanism to the microscopic details of Assyrian seals, these technologies demonstrate systematic approaches to precision that rival modern industrial methods. The evidence suggests that ancient craftsmen possessed not just individual skill, but systematic knowledge of precision techniques that could be taught and replicated. The consistency of quality across different examples implies standardized methods and quality control systems that enabled reliable production of complex optical instruments and precision artifacts. The loss of these ancient optical technologies represents one of history's significant intellectual casualties. When traditional knowledge systems were disrupted by political upheaval, cultural change, or technological displacement, the accumulated wisdom of generations vanished within decades. The challenge for modern science is not just to understand what ancient craftsmen achieved, but to recover the knowledge systems that made these achievements possible. As we examine these ancient optical mysteries, we must confront the humbling recognition that our ancestors possessed technical knowledge that we are still struggling to comprehend. The precision evident in their work suggests understanding of optical principles that parallels modern scientific knowledge, achieved through practical experience and systematic investigation that challenge our assumptions about the development of science and technology. From these optical mysteries, where ancient craftsmen bent light to serve human purposes with impossible precision, our investigation now leads us to another realm of ancient achievement that challenges modern understanding. The energy and mechanical systems that reveal knowledge of automation, acoustics, and power generation that seems centuries ahead of its time. Energy and automation. Ancient power systems. From the realm of ancient optics, where light itself was commanded by forgotten masters to serve human purposes with impossible precision, we now venture into perhaps the most controversial territory of ancient technological achievement. Here, in the shadowed workshops where craftsmen once harnessed forces that modern science is only beginning to understand, we encounter evidence of energy systems and mechanical automation that challenge every assumption about the capabilities of pre-industrial civilizations. These are not merely clever mechanical devices or ingenious applications of simple principles, but sophisticated systems that suggest understanding of energy, automation, and power generation that seems to transcend the supposed limitations of their time. The mysteries we are about to explore exist at the intersection of physics and archaeology, where ancient artifacts whisper of capabilities that conventional history cannot explain. From clay jars that generate electricity to buildings that amplify sound with acoustic perfection, from temples that operated with mechanical precision to hydraulic systems that lifted massive stones, the evidence suggests that our ancestors possessed knowledge of energy manipulation that modern science has only recently begun to appreciate. The Baghdad Battery, ancient electrochemistry. In the dusty storage rooms of the Baghdad Museum, where countless artifacts wait patiently for scholars to unlock their secrets, sits a collection of clay jars that have sparked one of archaeology's most heated debates. Discovered in 1936 at Qujut Rabu, Iraq, these humble containers, consisting of clay vessels containing copper cylinders, iron rods, and asphalt seals, have been thrust into the center of a controversy that strikes at the heart of our understanding of ancient technological capabilities. The objects themselves appear unremarkable at first glance. Dating to the Parthian period between 250 BCE and 250 CE, they consist of terracotta jars about 14 centimeters tall, each containing a copper cylinder with an iron rod suspended inside. The cylinders are sealed with asphalt, and the entire assemblage shows signs of corrosion that suggests the presence of an acidic solution. When German archaeologist Wilhelm Koenig first examined these artifacts in 1940, he made a startling observation. When filled with an acidic solution, these assemblages generate electrical current. Modern replicas of the Baghdad battery produce between 0.5 and 1.1 volts of electrical potential, a modest but measurable output that has led to decades of speculation about ancient electrochemical knowledge. The electroplating theory, first proposed by Koenig, suggests that these devices were used for gold-plating silver objects, a process that would explain the thin gold layers found on some ancient artifacts. The idea that ancient craftsmen possessed electrochemical knowledge centuries before Luigi Galvani's famous experiments with frog legs has captured imaginations and sparked intense scholarly debate. However, the deeper we delve into the Baghdad battery mystery, the more complex the truth becomes. Modern archaeological analysis has revealed that many of the artifacts interpreted as evidence of electroplating were actually fire-gilded using mercury, a technique well documented in ancient texts and requiring no electrical current. No confirmed electroplated objects from the Parthian period have been discovered, despite extensive searches of museum collections worldwide. The recent scholarly consensus has shifted toward interpreting these objects as scroll containers, similar to thousands of others found throughout Mesopotamia. The copper, iron, and asphalt all possessed magical and protective associations in ancient cultures, suggesting that their combinations served ritual rather than technological purposes. The weak electrical output of modern replicas, insufficient for practical electroplating even when connected in series, further undermines the battery theory. Yet the mystery persists not in what these objects actually were, but in what they represent about human technological experimentation. Whether or not the ancient Mesopotamians intended to create electrical devices, the fact remains that they assembled materials that generate electrical current when properly activated. This achievement, whether accidental or intentional, demonstrates the sophisticated understanding of materials and chemical processes that characterized ancient craftsmanship. Acoustic architecture, buildings that amplify sound. Far from the electrochemical controversies of Mesopotamia, in the limestone amphitheaters of ancient Greece and the towering temples of Maya civilization, we encounter evidence of acoustic engineering that rivals modern sound system design. Here, ancient architects created structures that function as architectural instruments, manipulating sound waves with precision that seems to exceed the capabilities of their time. The Theater of Epidaurus in Greece stands as perhaps the most celebrated example of ancient acoustic mastery. Built in the 4th century BCE, this limestone amphitheater can transmit perfect speech from the stage to 14,000 spectators without any form of amplification. The acoustic properties are so precise that a coin dropped on the stage can be heard clearly in the uppermost rows, while normal conversation becomes inaudible beyond a few meters. The secret lies in the theater's sophisticated understanding of sound propagation principles. The limestone construction acts as both natural amplifier and acoustic filter, creating unique reflection patterns that enhance speech frequencies while suppressing background noise. The stepped seating creates a series of acoustic mirrors that focus sound waves toward the audience, while the material properties of the limestone filter out lower frequencies associated with crowd noise and environmental sounds. Recent research by Dr. Nico de Klerk at the Georgia Institute of Technology has revealed the mathematical precision underlying these acoustic properties. The theater's design incorporates principles of wave interference and frequency filtering that wouldn't be formally understood until the development of modern acoustics. The corrugated surface of the limestone seating creates periodic structures that act as acoustic filters, demonstrating understanding of wave physics that seems centuries ahead of its time. But the acoustic achievements of ancient civilizations extend far beyond Greek theaters. In the jungles of Mexico, Maya architectural complexes demonstrate equally sophisticated understanding of sound manipulation. Research by Dr. Francisca Zalaquet at the National Autonomous University of Mexico has revealed that Palenque's northern group functioned as architectural sound amplification systems, projecting speech across distances exceeding 100 meters without electronic enhancement. The Maya understanding of acoustics enabled them to create complex soundscapes using architectural design principles. The Pyramid of Kukulkan at Chichen Itza produces an echo resembling a quetzal bird's chirp when people clap at its base, an acoustic effect that was intentionally engineered into the structure's design. The integration of sound engineering with religious symbolism demonstrates sophisticated understanding of both acoustic principles and human psychology. At Chavín de Huántar in Peru, ancient architects created an underground labyrinth designed to disorient visitors while amplifying supernatural sound effects. The irregular stone surfaces create complex acoustic reflections that transform simple sounds into otherworldly experiences. Combined with the use of psychoactive substances, these acoustic effects created immersive sensory experiences that served religious and ceremonial purposes. The precision required for these acoustic achievements suggests systematic understanding of sound propagation that parallels modern architectural acoustics. The ability to predict and control acoustic properties through architectural design implies mathematical modeling capabilities that seem impossible for pre-scientific civilizations. Ancient automation, self-operating temples. In the workshops of ancient Alexandria, where the greatest minds of the classical world gathered to push the boundaries of human knowledge, Hero of Alexandria created mechanical marvels that would not be matched for over a millennium. His automated devices, temple doors that opened by themselves, fountains that flowed on command, and statues that moved with lifelike grace, represent the pinnacle of ancient mechanical engineering and demonstrate understanding of automation principles that seem centuries ahead of their time. Hero's pneumatic and hydraulic systems powered a wide range of automated devices that served both practical and ceremonial purposes. His automatic temple doors opened when fires were lit on altars, using the expansion of heated air to operate hidden mechanisms. Holy water dispensers activated when coins were inserted, creating self-operating vending machines that funded temple operations. Mechanical birds sang at predetermined times, while automated trumpets announced religious ceremonies with clockwork precision. The complexity of these systems required sophisticated understanding of mechanical principles that wouldn't be formally codified until the Renaissance. Hero's devices incorporated gear trains, linkages, and control systems that demonstrate knowledge of mechanical advantage, timing mechanisms, and feedback control that rivals modern automation technology. The precision manufacturing required for ancient automation systems exceeded what should have been possible with available technology. Bronze gears were cut to tolerances measured in fractions of millimeters, while complex assemblies required advanced metallurgical knowledge to create durable mechanical components. The level of precision achieved suggests systematic production methods that approach modern industrial standards. Roman temple automation incorporated even more sophisticated systems, combining hydraulic power with pneumatic control to create dramatic effects during religious ceremonies. Water-powered mechanisms operated temple doors, activated mechanical statues, and created special effects that enhanced the spiritual experience of worshippers. These systems demonstrate understanding of fluid mechanics and mechanical engineering that challenges assumptions about ancient technological capabilities. The precision timing mechanisms incorporated into ancient automation systems suggest understanding of mechanical principles that parallel modern clockwork technology. The ability to coordinate multiple mechanical operations with precise timing implies systematic approaches to mechanical design that seem impossible for pre-industrial civilizations. Hydraulic mysteries. Ancient water power. The mastery of hydraulic engineering achieved by ancient civilizations represents one of their most sophisticated technological achievements. From the precision water clocks of ancient China to the massive stone lifting systems recently discovered in Egypt, these hydraulic technologies demonstrate understanding of fluid mechanics and precision engineering that challenges our assumptions about ancient capabilities. Chinese water clocks from the 8th century CE incorporated water wheel-controlled timing mechanisms that represented the world's most accurate timekeeping devices for nearly 2,000 years. These sophisticated instruments used carefully calibrated water flows to operate complex mechanical systems that track time with precision that wouldn't be exceeded until the development of modern mechanical clocks. The precision required for accurate water clock operation demanded understanding of fluid dynamics that parallels modern hydraulic engineering. The devices incorporated feedback control systems using floats and overflow mechanisms, with automatic seasonal adjustments that compensated for varying day lengths throughout the year. The level of precision achieved suggests systematic understanding of hydraulic principles that seems centuries ahead of its time. A revolutionary discovery in 2024 has revealed that ancient Egyptian engineers incorporated sophisticated hydraulic systems into pyramid construction. The step pyramid of Djoser included an advanced water management system that functioned as both construction aid and ceremonial complex. The The Jisr Elmuter enclosure operated as a check dam and water treatment facility, creating a temporary lake system that surrounded the pyramid complex during construction. This hydraulic elevation system lifted stones using water pressure in a process that researchers describe as volcano fashion, lifting from the pyramid's interior. The engineering sophistication rivals modern water treatment plants, incorporating settling basins, retention systems, and purification components with quality control systems that ensured consistent operation. The integration of hydraulic power with construction logistics represents advanced engineering that challenges assumptions about ancient construction techniques. The ability to coordinate massive hydraulic systems with precision stone placement suggests project management capabilities that rival modern construction projects. Electromagnetic anomalies, ancient energy fields. At the intersection of ancient architecture and natural phenomena, researchers have discovered electromagnetic anomalies that suggest possible ancient understanding of energy fields that modern science is only beginning to investigate. While the evidence remains controversial, the patterns emerging from these studies hint at knowledge systems that may have incorporated subtle energy phenomena into architectural and engineering design. Stonehenge exhibits measurable magnetic anomalies that correlate with its astronomical alignments and underlying geological features. The monument's builders may have been aware of these natural phenomena, incorporating them into the structures designed for purposes that remain mysterious. The precision of the astronomical alignments combined with the magnetic properties suggests possible integration of multiple natural phenomena into a unified system. The Great Pyramid of Giza contains granite chambers with quartz crystals that possess piezoelectric properties, the ability to generate electrical current when subjected to mechanical stress. While no conclusive evidence exists for intentional electromagnetic manipulation, the combination of materials and geometric arrangements creates measurable electromagnetic effects that continue to intrigue researchers. Ancient Chinese compass development demonstrates sophisticated understanding of magnetic phenomena centuries before European magnetic knowledge. The integration of magnetic navigation with astronomical observation suggests systematic investigation of natural phenomena that may have encompassed broader understanding of electromagnetic principles. The relationship between ancient monuments and natural energy phenomena remains one of archaeology's most controversial areas of investigation. While the evidence is circumstantial, the patterns suggest that ancient builders may have possessed knowledge of subtle environmental effects that influenced their architectural decisions. The automation legacy. The energy and automation systems of ancient civilizations reveal a pattern of technological achievement that challenges conventional understanding of pre-industrial capabilities. From the electrochemical experiments of Mesopotamian craftsmen to the acoustic engineering of Greek architects, from the mechanical automation of Alexandrian inventors to the hydraulic systems of Egyptian engineers, these achievements demonstrate systematic understanding of energy manipulation that parallels modern engineering knowledge. The precision evident in these ancient systems suggests not just individual genius, but systematic knowledge transmission that enabled consistent reproduction of complex technologies. The global distribution of similar achievements implies either independent development of comparable techniques or knowledge transfer systems that connected ancient civilizations across vast distances. The loss of these ancient energy technologies represents one of history's significant intellectual tragedies. When traditional knowledge systems were disrupted by political upheaval, cultural change, or technological displacement, the accumulated wisdom of generations vanished within decades. The challenge for modern science is not just to understand what ancient engineers achieved, but to recover the knowledge systems that made these achievements possible. As we examine these ancient energy and automation systems, we must confront the humbling recognition that our ancestors possessed technical knowledge that we are still struggling to comprehend. The sophistication evident in their work suggests understanding of energy manipulation principles that parallel modern scientific knowledge, achieved through practical experience and systematic investigation that challenge our assumptions about the development of technology and human capability. From these ancient power systems, where our ancestors harnessed forces that modern science is still investigating, our journey now leads us to another realm of extraordinary achievement: the celestial mastery demonstrated by ancient astronomers and navigators whose precision in mapping the heavens and traversing the oceans seems to exceed the capabilities of their time. Celestial mastery, navigation, and astronomy. From the workshops where ancient engineers harnessed terrestrial forces through hydraulic systems and mechanical automation, We now lift our gaze to the heavens, where our ancestors achieved feats of astronomical precision that humble modern science. If the energy systems we have examined reveal mastery over earthly forces, the celestial technologies of ancient civilizations demonstrate something far more profound: the ability to decode the language of the cosmos itself, to navigate vast oceanic distances using only the stars as guides, and to predict celestial events with accuracy that wouldn't be matched until the computer age. The night sky that our ancestors observed was the same canvas of stars that modern astronomers study through powerful telescopes and sophisticated instruments. Yet somehow, using nothing more than naked-eye observation and mathematical genius, ancient civilizations achieved astronomical precision that seems to transcend the limitations of their tools. They mapped stellar positions with accuracy measured in degrees, predicted planetary movements across centuries, and created navigation systems that enabled traversal of thousands of oceanic miles without losing their way. These achievements represent not just impressive observations, but systematic scientific investigation that challenges every assumption about the development of human knowledge. Polynesian navigation, mental GPS systems. In the vast expanse of the Pacific Ocean, where modern sailors rely on GPS satellites and electronic instruments to find their way, the ancestors of Polynesian navigators accomplished something that seems impossible to contemporary minds. Using nothing more than their understanding of stars, waves, and natural phenomena, they navigated across thousands of miles of open ocean with precision that rivals modern navigation systems, settling islands across 10,000 miles of Pacific waters in one of history's most remarkable achievements of human exploration. The Polynesian navigation system, known as wayfinding, represents perhaps the most sophisticated non-instrumental navigation technology ever developed. These master navigators, called Paulu in Carolinian tradition, created mental maps of extraordinary complexity that treated the ocean not as an empty void, but as a highway marked by invisible signposts that only they could read. The attack system conceptualized islands as reference points on a moving mental grid, where navigators tracked their position relative to known landmarks using a three-dimensional model that existed entirely in their minds. The precision of this system defies modern understanding. Traditional navigators could determine their position within a few miles after weeks at sea, using techniques that combined multiple environmental indicators in ways that modern science is only beginning to appreciate. They read wave patterns with extraordinary sensitivity, detecting the subtle reflections and refractions caused by distant islands that were still beyond the horizon. Cloud formations revealed the presence of land through the way they gathered and moved above unseen atolls, while the flight patterns of seabirds provided directional guidance that extended their effective range of detection. The star compass system represents one of navigation's most remarkable intellectual achievements. Polynesian navigators memorized the rising and setting positions of hundreds of stars, creating mental models that functioned as precise directional instruments. These star lines connected specific celestial objects to geographic bearings, enabling navigators to maintain accurate headings throughout the night. The system was so sophisticated that it incorporated corrections for seasonal changes in star positions, magnetic declination, and the effects of current and wind drift. Modern GPS tracking of traditional navigators has revealed accuracy levels that astonish contemporary pilots and sailors. Computer modeling of traditional wayfinding techniques confirms their effectiveness, while attempts by modern navigators to learn these ancient methods reveal the extraordinary skill and knowledge required for their application. The precision achieved suggests not just individual talent, but systematic knowledge transmission that preserved complex information across generations through oral tradition alone. The navigational achievements of Polynesian wayfinders represent more than just practical seamanship. They demonstrate cognitive capabilities that challenge our understanding of human potential. The ability to maintain complex three-dimensional mental maps while processing multiple environmental variables simultaneously suggests intellectual achievements that parallel modern computational systems. These navigators were living GPS units, capable of calculating position, direction, and estimated arrival times using only their trained senses and accumulated knowledge. Maya astronomical precision, calculations beyond instruments. In the stone cities of the Maya civilization, where towering pyramids pierced the jungle canopy like ancient observatories, astronomer priests achieved computational precision that would not be equaled until the development of modern astronomy. Working without telescopes, mechanical calculators, or precision instruments, Maya astronomers tracked planetary movements with accuracy that exceeds ancient European achievements and rivals contemporary observations made with sophisticated equipment. The Dresden Codex, one of the few surviving Maya books, contains astronomical tables that demonstrate mathematical precision so extraordinary that it challenges every assumption about ancient scientific capabilities. The Venus table tracks the planet's 584-day synodic period with an error of only 0.08 days, a level of accuracy that requires systematic observations spanning multiple generations and mathematical computation that approaches modern standards. The Maya achievement becomes even more remarkable when we consider the scope of their astronomical knowledge. Their calculations for Mars observations exceeded the precision of Ptolemy's work, while their tracking of Jupiter and Saturn demonstrated long-term accuracy spanning centuries. The Maya astronomer-mathematicians somehow managed to extract precise planetary periods from the complex apparent motions visible from Earth, requiring mathematical techniques that seem impossible for pre-telescopic astronomy. Recent analysis has revealed that the Maya 819-day calendar represents far more than previously understood. Published research in ancient Mesoamerica demonstrates that this calendar actually tracks planetary movements over 20 complete cycles, approximately 45 years, with all visible planets completing whole-number synodic periods within this expanded framework. This discovery reveals mathematical sophistication that transforms our understanding of Maya astronomical achievement. The precision required for these calculations would seemingly demand instruments capable of measurements beyond known ancient capabilities. Yet the Maya achieved this accuracy through systematic observation and mathematical manipulation that suggests advanced understanding of orbital mechanics paralleling modern astronomical knowledge. Their long-count calendar tracked time over 5,125 years with precision that differs from modern calculations by only 0.0002 days, an achievement that rivals atomic clock accuracy. The mathematical framework underlying Maya astronomy demonstrates understanding of complex periodicities and their interactions that wouldn't be formally developed until Kepler's work on planetary motion. The ability to calculate long-term planetary positions and predict eclipses with such precision suggests not just careful observation, but theoretical understanding of celestial mechanics that seems centuries ahead of its time. The Maya astronomer priests achieved these calculations without the benefit of algebraic notation, decimal systems, or mechanical aids. Their vigesimal-based 20 mathematical system, combined with sophisticated geometric understanding, enabled computational achievements that challenge our assumptions about the relationship between mathematical notation and analytical capability. The precision of their results suggests cognitive approaches to mathematical problem-solving that may have been more sophisticated than contemporary methods. Ancient star maps, 40,000 years of astronomical knowledge. The history of human astronomical achievement extends far deeper into the past than conventional archaeology suggests. From the cave paintings of Lascaux to the stone circles of Göbekli Tepe, from the astronomical alignments of megalithic monuments to the sophisticated star charts of medieval civilizations, evidence emerges of systematic astronomical observation that spans tens of thousands of years. The Dunhuang star chart, dating to the 7th century CE, represents the oldest complete preserved star map from any civilization. This remarkable document contains over 1,300 individual stars plotted with accuracy ranging from 1.5 to 4 degrees for the brightest objects, precision that approaches early telescopic observations. The chart employs stereographic projection techniques that demonstrate advanced mathematical understanding centuries before similar methods appeared in European astronomy. The systematic nature of ancient astronomical observation becomes evident when we examine the global distribution of astronomical sites and artifacts. Paleolithic cave paintings at Lascaux and Altamira appear to show constellation patterns, with dots positioned above animal figures that align with star clusters like the Pleiades. The precision of these alignments suggests not accidental correlation, but deliberate astronomical recording that dates to 17,000 years ago. Göbekli Tepe in Turkey demonstrates precise astronomical alignments dating to 11,600 years ago, making it the world's oldest known astronomical observatory. The massive stone pillars are oriented to cardinal directions with accuracy that rivals modern surveying, while the circular arrangements appear to function as a sophisticated lunisolar calendar system. Recent analysis suggests the site represents humanity's earliest known calendar, predating similar achievements by over 1,000 years. The Ishango bone from the Congo, dating to 22,000 years ago, contains mathematical notations that correspond to lunar cycles and may represent humanity's oldest astronomical calculation system. The bone's markings suggest systematic tracking of celestial periodicities that demonstrates cognitive capabilities previously thought impossible for the period. These ancient astronomical achievements suggest that systematic observation of celestial phenomena has been a continuous human activity for tens of thousands of years. The precision evident in ancient star maps and astronomical alignments implies not just casual sky watching, but dedicated scientific investigation that preserved and transmitted knowledge across millennia. Megalithic observatories, stone computers. Across the landscapes of ancient Europe, massive stone monuments stand as testament to astronomical knowledge that required multi-generational planning and construction. These megalithic observatories represent more than impressive engineering achievements. They function as analog computers designed to track celestial cycles with precision that rivals modern instrumentation. Stonehenge stands as perhaps the most sophisticated example of megalithic astronomical engineering. The monument's main axis aligns precisely with summer solstice sunrise and winter solstice sunset, while the station stones form a perfect rectangle that is geometrically possible only at Stonehenge's specific latitude. This level of precision required understanding of Earth's spherical geometry and the sun's annual path that seems impossible for Neolithic builders. The complexity of Stonehenge's astronomical functions extends far beyond simple solar alignments. The Aubrey holes, a circle of 56 chalk pits, appear to track the 56-year cycle of lunar eclipses, suggesting understanding of complex astronomical periodicities that wouldn't be formally described until modern times. The monument's designers somehow managed to encode multiple astronomical cycles into a single stone structure that functioned as a comprehensive celestial calculator. The precision required for Stonehenge's construction challenges our understanding of ancient surveying capabilities. The monument's alignments are accurate to fractions of degrees, requiring measurement techniques that seem impossible without sophisticated instruments. The transportation and positioning of massive stones with such precision suggests construction techniques that remain largely mysterious. Nabta Playa in Egypt's Sahara Desert represents another remarkable example of ancient astronomical engineering. Dating to 7,000 years ago, this stone circle predates Stonehenge by 2,000 years while demonstrating equally sophisticated astronomical knowledge. The site's alignments to cardinal directions and celestial events suggest systematic astronomical observation in ancient Africa that challenges assumptions about the development of scientific knowledge. The global distribution of megalithic observatories implies either independent development of comparable astronomical knowledge or communication networks that connected ancient civilizations across vast distances. The consistency of astronomical precision across different cultures and time periods suggests systematic approaches to celestial observation that represent genuine scientific achievement. The computational challenge. The astronomical achievements of ancient civilizations present a fundamental challenge to our understanding of human cognitive capabilities. The precision evident in their observations and calculations suggests intellectual achievements that rival modern computational systems, accomplished through purely mental processes and systematic observation techniques. The mathematical requirements for ancient astronomical achievements appear to exceed the capabilities of their supposed technological context. Predicting eclipses requires understanding of complex orbital mechanics, while maintaining accurate calendars demands mathematical precision that seems impossible without mechanical aids. Yet ancient astronomers accomplished these feats through systematic observation and mathematical manipulation that challenges our assumptions about the relationship between technology and scientific achievement. The preservation of astronomical knowledge across millennia suggests information transmission systems that were more sophisticated than oral tradition alone. The consistency of astronomical precision across cultures and time periods implies systematic approaches to knowledge preservation that enabled complex information to survive cultural disruptions and generational changes. The cognitive achievements represented by ancient astronomy demonstrate human intellectual capabilities that challenge modern understanding of cognitive limits. The ability to maintain complex astronomical models while processing multiple variables simultaneously suggests mental achievements that parallel modern computational systems. accomplished through training and systematic knowledge transmission that enabled extraordinary human performance. Celestial legacy. The astronomical and navigational achievements of ancient civilizations reveal patterns of precision and systematic knowledge that challenge every assumption about pre-modern capabilities. From the mental GPS systems of Polynesian navigators to the computational precision of Maya astronomers, from the 40,000-year history of star mapping to the stone computers of megalithic builders, these achievements demonstrate scientific investigation that rivals modern methodology. The precision evident in ancient astronomical work suggests not just individual genius, but systematic knowledge transmission that enabled consistent reproduction of complex observations and calculations. The global distribution of comparable achievements implies either independent development of similar techniques or communication networks that connected ancient civilizations across vast distances. The loss of many ancient astronomical techniques represents one of history's significant intellectual tragedies. When traditional knowledge systems were disrupted by cultural change or technological displacement, the accumulated wisdom of millennia vanished within generations. The challenge for modern science is not just to understand what ancient astronomers achieved, but to recover the knowledge systems that made these achievements possible. As we examine these ancient celestial mastery systems, we must confront the humbling recognition that our ancestors possessed scientific knowledge that we are still struggling to comprehend. The precision evident in their work suggests understanding of astronomical principles that parallel modern scientific knowledge, achieved through systematic observation and mathematical analysis that challenge our assumptions about the development of human knowledge. From these ancient observatories, where our ancestors decoded the language of the cosmos with impossible precision, our investigation now leads us to another realm of extraordinary achievement: the chemical mastery demonstrated by ancient civilizations whose molecular manipulations and preservation techniques continue to outperform modern alternatives in ways that challenge our understanding of materials science and biochemistry. Chemical secrets. Ancient molecular mastery. From the ancient observatories where our ancestors decoded the celestial language written across the night sky, we now descend into the laboratories and workshops where they commanded forces even more fundamental: the very molecules that compose matter itself. If their astronomical achievements demonstrate mastery over cosmic cycles spanning millennia, their chemical accomplishments reveal something equally extraordinary: the ability to manipulate matter at the molecular level with precision that modern science is still struggling to understand and replicate. In the shadowed chambers where ancient chemists practiced their art, where embalmers preserved bodies for eternity and metallurgists created materials that outlast contemporary alternatives, we encounter evidence of molecular mastery that challenges every assumption about the development of chemistry. These were not crude experiments or accidental discoveries, but systematic applications of chemical knowledge that demonstrate understanding of molecular processes, pharmaceutical chemistry, and materials science that seems impossible for civilizations that supposedly lacked modern scientific theory. The evidence lies scattered across archaeological sites worldwide: concrete structures that heal their own cracks after 2 millennia, preserved mummies whose tissues remain intact despite thousands of years of exposure, surgical procedures performed with anesthetic precision that rivals modern medicine, and pigments that retain their brilliance while contemporary colors fade within decades. These achievements represent not just impressive practical results, but evidence of chemical knowledge systems that integrated theoretical understanding with practical application in ways that modern science is only beginning to appreciate. Roman concrete, the self-healing stone. In the harbors of the Mediterranean, where ancient Roman ports still function after 2,000 years of service, we witness one of history's most remarkable achievements in materials science. While modern concrete structures require constant maintenance and often fail within decades, Roman concrete has not merely survived. It has grown stronger with age, developing properties that seem to mock our contemporary understanding of cement chemistry. The mystery of Roman concrete's extraordinary durability has puzzled engineers for centuries. Modern Portland cement, the standard for contemporary construction, begins to deteriorate almost immediately upon exposure to seawater and weather. Yet Roman harbors, aqueducts, and buildings continue to function with structural integrity that surpasses many modern constructions. The Pantheon in Rome, built with Roman concrete 1,900 years ago, remains the world's largest unreinforced concrete dome. Its structure is sound today as when Emperor Hadrian first walked beneath its soaring vault. The breakthrough that solved this ancient mystery came in 2023, when researchers at MIT and Harvard published findings that revolutionized our understanding of Roman construction technology. The secret lies in what the Romans called limeclasts, chunks of quicklime that create a self-healing mechanism within the concrete matrix. When cracks develop in the structure, water penetrates and reacts with these limeclasts, forming new calcium carbonate crystals that automatically seal the damage. This self-healing capability results from the Romans' hot mixing technique, where quicklime was combined directly with water and volcanic ash in a process that modern concrete producers had dismissed as primitive. The Romans' method creates a hierarchical structure with limeclasts distributed throughout the concrete like microscopic repair kits, waiting to activate when the structure needs healing. Additionally, their use of volcanic ash, pozzolan from the slopes of Mount Vesuvius, provides long-term strength development through chemical reactions that continue for centuries. The chemical sophistication of Roman concrete extends beyond its self-healing properties. When exposed to seawater, the volcanic ash reacts with dissolved minerals to form beneficial compounds that actually strengthen the concrete over time. This process, which modern chemistry calls pozzolanic reaction, transforms what would be destructive salt exposure into a strengthening mechanism that enhances the structure's durability. The environmental implications of this ancient technology are staggering. The concrete industry currently produces 8% of global carbon emissions, largely due to the energy-intensive production of Portland cement. Roman techniques, which operate at lower temperatures and use locally available materials, could dramatically reduce construction's environmental impact while creating structures that last millennia rather than decades. The rediscovery of Roman concrete principles represents more than archaeological curiosity. It's technological recovery that could transform modern construction. Several companies are now developing Roman-inspired concrete formulations for commercial applications, suggesting that ancient wisdom may provide solutions to contemporary challenges that modern technology created but cannot solve. Mummification chemistry, preserving the impossible. In the desert workshops of ancient Egypt, where the sacred art of mummification transformed human mortality into eternal preservation, chemists working without knowledge of microbiology achieved preservation techniques that modern science struggles to replicate. The mummies that emerged from these ancient laboratories represent one of history's most sophisticated achievements in biochemistry: the indefinite preservation of organic tissue through chemical processes that demonstrate molecular mastery centuries ahead of its time. A groundbreaking 2023 study of the Saqqara Embalming Workshop revealed the extraordinary complexity of ancient Egyptian preservation chemistry. Dr. Stephen Buckley's analysis of 121 ceramic bowls and cups used in mummification uncovered evidence of chemical formulations that rival modern pharmaceutical preparations in their precision and effectiveness. These ancient chemists had developed multi-step processes that addressed every aspect of tissue preservation through systematic application of chemicals whose properties they understood through generations of practical experience. The chemical arsenal employed by ancient embalmers demonstrates sophisticated understanding of antimicrobial chemistry. Ricinoleic acid from castor oil provided powerful antiseptic and antifungal properties, while complex mixtures of pine resin, bitumen, and beeswax created hydrophobic barriers that prevented moisture penetration. The use of natron, a naturally occurring mixture of sodium carbonate, sodium bicarbonate, and sodium sulfate, created high pH environments exceeding 12 that halted bacterial growth while preserving tissue structure through chemical dehydration. The precision required for successful mummification reveals understanding of quantitative chemistry that seems impossible for ancient practitioners. The process demanded exact timing for chemical treatments, precise temperature control during natron processing, and careful pH management to achieve optimal preservation without damaging delicate tissues. Modern attempts to replicate ancient mummification techniques consistently fail to achieve the quality of preservation evident in ancient examples. Recent research has revealed that ancient embalmers used natron in solution rather than dry powder, a technique that creates more effective preservation through controlled chemical reactions. The discovery overturns decades of scholarly assumptions about ancient methods and demonstrates that Egyptian chemists understood principles of solution chemistry that weren't formally described until modern times. The sophistication of ancient preservation chemistry extends to specialized techniques for different body parts and social classes. Brain tissue required different chemical treatments than muscle or bone, while the preservation of royal mummies involved additional steps that enhanced both preservation quality and symbolic significance. The ancient embalmers had developed what amounts to a complete system of biochemical preservation that addressed every aspect of organic decay through systematic chemical intervention. The chemical knowledge embodied in mummification represents more than preservation technique. It demonstrates understanding of molecular processes that parallels modern biochemistry. The embalmer's ability to halt decomposition while maintaining tissue structure suggests knowledge of enzyme chemistry, protein preservation, and cellular biology that challenges assumptions about ancient scientific understanding. Ancient anesthesia, surgery without pain. In the surgical centers of ancient civilizations, where operations were performed with precision that rivals modern technique, physician-chemists developed anesthetic protocols that enabled complex procedures centuries before the official discovery of surgical anesthesia in the 19th century. These ancient practitioners possessed pharmaceutical knowledge that combined multiple drug compounds in sophisticated formulations that achieved surgical anesthesia with remarkable precision and safety. The most sophisticated ancient anesthesia system developed in Japan, where Dr. Seishu Hanaka performed the world's first documented mastectomy under general anesthesia in 1804, 42 years before Ether Day in the West. Hanaka's technique employed a complex herbal mixture called mafutsusen, containing tropane alkaloids from datura and other plants that created surgical anesthesia comparable to modern techniques. The precision required for this system was extraordinary, as the therapeutic window between effective anesthesia and lethal overdose was extremely narrow. The Japanese anesthesia tradition traced its origins to ancient Chinese medicine, where surgeon Hua Tuo had used similar techniques between 140 and 208 CE. The Mafizan formula combined multiple psychoactive compounds in precise proportions that achieved surgical anesthesia while maintaining vital functions. The technique was so successful that it was revived during China's Cultural Revolution, when it was used in over 46,000 surgeries during the 1960s and 1970s due to Western anesthetic shortages. Roman military hospitals developed equally sophisticated anesthesia protocols using combinations of mandrake, poppy, and henbane. These multi-drug formulations demonstrate understanding of pharmacological synergy that parallels modern anesthetic practice. Dedicated anesthesia specialists, known as medicus ordinarius, administered complex mixtures that included local anesthetics like memphitic stone and henbane seeds for regional nerve blocks. The chemical precision required for ancient anesthesia challenges our understanding of pharmaceutical knowledge in pre-scientific societies. The active compounds involved, hyoscyamine, scopolamine, atropine, and morphine, require exact dosing to achieve anesthesia without causing respiratory depression or cardiac arrest. Ancient practitioners somehow developed protocols that reliably achieved surgical anesthesia using natural compounds whose pharmacology wouldn't be formally understood until modern chemistry. Ancient surgical texts describe anesthetic procedures with remarkable detail, including patient selection criteria, dosage calculations based on body weight, and post-operative care protocols that demonstrate systematic medical knowledge. The consistency of successful outcomes suggests standardized training systems that transmitted complex pharmaceutical knowledge across generations of practitioners. The sophistication of ancient anesthesia extends beyond drug formulation to include understanding of psychological factors that enhanced anesthetic effectiveness. Ancient practitioners combined chemical anesthesia with environmental controls, ritual elements, and psychological preparation that created comprehensive anesthetic experiences addressing both physical and mental aspects of surgical trauma. Lost pigments, colors that never fade. In the hidden workshops where ancient artists created colors that have retained their brilliance for millennia, master chemists developed pigment formulations that demonstrate molecular engineering centuries ahead of its time. While modern synthetic colors fade within decades of exposure to light and air, ancient pigments continue to glow with the intensity of freshly applied paint, their molecular structures remaining stable through chemical processes that modern materials science is still struggling to understand. Egyptian blue, the world's first synthetic inorganic pigment, represents one of chemistry's earliest triumphs. Created through precise stoichiometric reactions that required exact temperature control and atmospheric conditions, This calcium-copper tetrasilicate compound demonstrates understanding of quantitative chemistry that seems impossible for ancient practitioners. The synthesis process demanded temperatures exceeding 850 degrees Celsius maintained within narrow ranges, while the atmospheric conditions required reducing environments that prevented copper oxidation. The precision required for Egyptian blue production reveals sophisticated understanding of chemical thermodynamics and reaction kinetics. Modern attempts to recreate the ancient process consistently fail to achieve the quality and consistency evident in ancient examples. The pigment's extraordinary stability results from its molecular structure, which creates absorption and emission properties that give the color its characteristic brilliance while resisting photochemical degradation. Maya blue represents perhaps the most remarkable achievement in ancient pigment chemistry. This extraordinary blue color, which has retained its intensity for over 1,000 years in humid tropical conditions, results from a complex combination of indigo dye, palygorskite clay, and copal resin that creates molecular structures resembling modern biomimetic materials. The preparation process involved thermal treatments that created chemical bonds between organic and inorganic components, resulting in a hybrid material that exhibits properties exceeding either component alone. Recent research has revealed that Maya blue's durability results from molecular cage structures that protect the indigo dye from chemical degradation. The clay matrix creates microscopic environments that stabilize the organic colorant, while the resin provides additional protective barriers. This biomimetic approach to materials design parallels modern nanotechnology research, achieved through practical chemistry that demonstrates extraordinary understanding of molecular interactions. Ancient red and black inks demonstrate equally sophisticated chemical knowledge. Egyptian scribes developed iron-based inks that incorporated lead compounds as dryers, using chemical principles identical to those employed in 15th century European oil painting. The pH control required for stable ink formulation suggests understanding of acid-base chemistry that wasn't formally developed until modern times. The global distribution of similar pigment technologies suggests either independent development of comparable chemical knowledge or communication networks that transmitted complex chemical information across ancient civilizations. The consistency of chemical achievements across different cultures and time periods implies systematic approaches to materials chemistry that represent genuine scientific investigation. Pharmaceutical chemistry, ancient drug development. The pharmaceutical achievements of ancient civilizations demonstrate understanding of medicinal chemistry that parallels modern drug development. From the complex multi-drug formulations of traditional Chinese medicine to the precise chemical extractions of ancient Egyptian physicians, these practitioners developed therapeutic compounds that demonstrate systematic understanding of pharmacology, drug interaction, and chemical modification that enhances therapeutic effectiveness. Chinese Paoji processing techniques employed over 30 different methods for deliberately altering the chemical structures and pharmacological effects of medicinal plants. These processing methods, including stir-frying, calcining, steaming, and fermentation, modify molecular structures in ways that increase bioavailability, reduce toxicity, and enhance therapeutic effects through controlled chemical transformations. Modern pharmaceutical analysis has confirmed that ancient processing methods achieve chemical modifications that parallel contemporary drug development techniques. The ancient practitioners somehow understood that chemical modification could improve therapeutic effectiveness while reducing side effects, developing systematic approaches to pharmaceutical chemistry that wouldn't be formally understood until modern times. The precision evident in ancient pharmaceutical formulations suggests understanding of dosage-response relationships that rivals modern pharmacology. Ancient medical texts describe exact dosages, preparation methods, and administration protocols that demonstrate systematic investigation of therapeutic effectiveness through what amounts to ancient clinical trials. The molecular legacy. The chemical achievements of ancient civilizations reveal patterns of molecular mastery that challenge conventional understanding of pre-modern capabilities. From the self-healing concrete of Roman engineers to the preservation chemistry of Egyptian embalmers, from the anesthetic protocols of ancient surgeons to the pigment formulations of master artists, these achievements demonstrate systematic understanding of chemistry that parallels modern molecular science. The precision evident in ancient chemical work suggests not just individual expertise, but systematic knowledge transmission that enabled consistent reproduction of complex formulations and processes. The global distribution of comparable achievements implies either independent development of similar techniques or communication networks that transmitted complex chemical knowledge across ancient civilizations. The loss of many ancient chemical technologies represents one of history's most significant intellectual tragedies. When traditional knowledge systems were disrupted by cultural change or technological displacement, the accumulated wisdom of millennia vanished within generations. The challenge for modern science is not just to understand what ancient chemists achieved, but to recover the knowledge systems that made these achievements possible. As we examine these ancient chemical mysteries, we must confront the humbling recognition that our ancestors possessed molecular knowledge that we are still struggling to comprehend. The sophistication evident in their work suggests understanding of chemical principles that parallel modern scientific knowledge, achieved through systematic investigation and practical experience that challenge our assumptions about the development of chemistry and materials science. From these ancient laboratories where molecules were commanded with impossible precision, our investigation now leads us to the final realm of extraordinary achievement: the information systems through which ancient civilizations stored, transmitted, and preserved knowledge across millennia in ways that continue to challenge our understanding of data management and communication technology. Information systems, ancient data storage. From the molecular laboratories where ancient chemists commanded atoms with forgotten wisdom, we now venture into perhaps the most intellectually profound realm of ancient achievement: the sophisticated systems through which our ancestors stored, transmitted, and preserved knowledge across the vast expanse of time itself. If their chemical mastery reveals understanding of matter at its most fundamental level, their information technologies demonstrate something equally extraordinary: the ability to encode complex data in three-dimensional matrices, to preserve knowledge across millennia without degradation, and to create communication networks that spanned continents without electronic infrastructure. In the archives and repositories where ancient civilizations safeguarded their most precious resource, knowledge itself, we encounter evidence of information management systems that challenge every assumption about the development of data storage and communication technology. These are not primitive record-keeping methods or crude attempts at documentation, but sophisticated approaches to information encoding, transmission, and preservation that in some cases exceed the capabilities of contemporary digital systems. The mysteries we are about to explore exist at the intersection of mathematics and memory, where abstract concepts were transformed into tangible objects that could survive the collapse of civilizations and the passage of millennia. From three-dimensional databases encoded in knotted cords to undeciphered scripts that guard their secrets with mathematical precision. From preservation systems that outlast modern media to communication networks that connected ancient worlds, the evidence suggests that our ancestors developed information technologies that represent genuine innovations in human knowledge management. Quipu, the three-dimensional database. In the high mountain archives of the Inca Empire, where administrative efficiency reached levels that would impress modern bureaucracies, a revolutionary information storage system encoded the complexities of an entire civilization in arrangements of knotted cords that functioned as three-dimensional databases. The Quipu, from the Quechua word meaning knot, represents one of history's most sophisticated information storage technologies, a system so complex and multifaceted that 500 years of intensive study have barely begun to unlock its secrets. The Quipu system employed pendant cords hanging from primary strings in arrangements that could contain up to 1,500 individual elements, each carrying multiple layers of encoded information. The basic numerical system operated on decimal principles, with different knot types representing different values and positional notation that paralleled modern place value systems. But the numerical capabilities were merely the foundation of a far more complex encoding system that incorporated color, cord material, knot positioning, spacing, and directional orientation to create multidimensional information matrices. The sophistication of Quipu encoding becomes apparent when we examine the precision required for their creation and interpretation. Individual Quipu could contain hundreds of statistical relationships, hierarchical data structures, and cross-referenced information that required systematic organization principles comparable to modern database design. The cord makers, known as Quipukamaics, were highly trained specialists who memorized not only the physical encoding systems but the oral interpretations that gave meaning to the encoded data. Recent breakthrough research by anthropologist Sabine Hyland achieved the first phonetic decipherment of Quipu words in 2017, proving conclusively that these systems could encode linguistic information beyond numerical data. Her analysis of a 17th-century quipu from San Juan de Calazzos revealed patterns that correspond to proper names mentioned in associated Spanish documents, demonstrating that quipu functioned as complete writing systems rather than mere accounting tools. Gary Urton's comprehensive database project at Harvard University has cataloged over 650 quipu, revealing mathematical patterns that suggest systematic information encoding comparable to digital systems. His analysis proposes that quipu employed binary principles in some applications, using directional variations and structural elements to create information storage capabilities that parallel modern computational approaches. The administrative applications of quipu encompassed the full spectrum of imperial governance. These three-dimensional databases recorded census data for millions of subjects, tribute obligations for thousands of communities, military logistics for vast armies, and historical narratives that preserved cultural memory across generations. The precision required for managing an empire spanning 2,500 miles of mountainous terrain through purely chord-based information systems demonstrates organizational capabilities that rival modern administrative technologies. The encoding density achievable through quipu systems approaches that of contemporary data storage media. A single large quipu could contain information equivalent to dozens of pages of text, encoded in a format that was portable, durable, and accessible to trained operators without requiring literacy in the conventional sense. The three-dimensional nature of the encoding enabled multiple information layers to coexist within the same physical structure. The loss of quipu reading ability represents one of history's most tragic destructions of information technology. When Spanish colonial authorities suppressed indigenous administrative systems, the knowledge required to interpret quipu vanished within a generation. The surviving quipu continue to hold their secrets, their encoded information tantalizingly visible but largely inaccessible to modern researchers who lack the interpretive keys that died with their creators. Undeciphered scripts, lost languages of the past. Scattered across archaeological sites worldwide lie examples of ancient writing systems that continue to guard their secrets with mathematical precision, representing information encoding technologies whose sophistication becomes more apparent as our analytical capabilities advance. These undeciphered scripts challenge our understanding of ancient communication systems while demonstrating approaches to information encoding that may represent innovations in symbolic representation that modern linguistics is still struggling to comprehend. Linear A, the script of the Minoan civilization that flourished in Crete from 1800 to 1450 BCE, represents one of archaeology's most persistent mysteries. This syllabic writing system contains approximately 90 distinct signs arranged in systematic patterns that demonstrate clear organizational principles. Yet the underlying language remains completely unknown. Recent computational analysis has identified recurring symbol patterns and frequency distributions that suggest sophisticated grammatical structures, but the absence of bilingual texts has prevented decipherment despite decades of intensive effort. The Indus Valley script presents even greater challenges to modern understanding. Dating from 3500 to 2000 BCE, this writing system appears on over 4,000 artifacts discovered across the vast Indus civilization, making it one of the world's earliest writing systems. The script contains over 400 unique symbols with statistical properties that suggest linguistic content. Yet the brevity of most inscriptions and the absence of lengthy texts has frustrated all attempts at decipherment. Computational linguistics has been applied to Indus script analysis with mixed results. Some researchers argue that the symbol frequency and arrangement patterns indicate a true writing system capable of encoding complete linguistic information, while others suggest the symbols represent a proto-writing system that conveyed limited semantic content without full grammatical structure. The controversy highlights the challenges inherent in analyzing information systems whose encoding principles remain unknown. Proto-Elamite represents another crucial mystery in the development of writing systems. Dating to approximately 3200 BCE, this script predates Sumerian cuneiform and may represent humanity's earliest attempt at systematic information encoding. The symbols were invented independently with no apparent precursors, yet they demonstrate organizational principles that suggest systematic approaches to information representation. Recent European research claims partial decipherment using silver vessel inscriptions, but the achievements remain controversial and incomplete. The Rongorongo script of Easter Island presents unique challenges due to its isolation and the limited survival of texts. Only 25 inscriptions remain, carved on wooden tablets using a Boustrophedon writing system where alternating lines read in opposite directions. The script contains approximately 120 symbols that appear to represent complete linguistic content. Yet the cultural disruption that accompanied European contact eliminated the knowledge necessary for interpretation. Modern attempts to decipher unknown scripts employ increasingly sophisticated analytical techniques, including artificial intelligence, pattern recognition algorithms, and computational linguistics. However, these technologies face fundamental limitations when applied to scripts whose linguistic foundations remain unknown. The absence of bilingual texts, the Rosetta Stones that enabled decipherment of Egyptian hieroglyphs and other ancient scripts, leaves many writing systems permanently beyond reach of modern analysis. The persistence of undeciphered scripts demonstrates the remarkable diversity of approaches that ancient civilizations developed for information encoding. Each system represents unique solutions to the challenge of converting spoken language into permanent visual symbols, suggesting cognitive innovations that may have exceeded contemporary understanding in their sophistication and efficiency. Long-term preservation, messages across millennia. The challenge of preserving information across vast spans of time has confronted every civilization that sought to transmit knowledge to future generations. Ancient solutions to this fundamental problem demonstrate understanding of material science, environmental factors, and information encoding that enabled successful preservation across millennia. Achievements that modern digital storage systems struggle to match despite technological sophistication. Stone carving represents perhaps the most successful ancient preservation technology, creating inscriptions that remain readable after 5,000 years of exposure to environmental extremes. The precision required for durable stone inscription demanded understanding of material properties, tool design, and carving techniques that optimized longevity without sacrificing readability. Ancient stonemasons developed systematic approaches to inscription depth, character spacing, and surface preparation that maximized preservation effectiveness. The selection of appropriate stone materials for inscription required sophisticated understanding of geological properties and environmental resistance. Ancient scribes chose stones based on hardness, grain structure, and chemical stability that would withstand specific environmental conditions for maximum preservation. The global consistency of successful stone inscription techniques suggests systematic knowledge transmission that preserved optimal carving methods across cultures and centuries. Ceramic and clay storage provided another highly successful preservation medium, protecting thousands of cuneiform tablets and papyrus documents for millennia. The chemical stability of properly fired ceramic creates storage environments that resist moisture, temperature fluctuation, and chemical degradation that destroys organic materials. Ancient potters developed clay formulations and firing techniques specifically optimized for document storage, creating preservation systems that function effectively for thousands of years. Metal preservation systems using bronze, gold, and specialized alloys provided corrosion-resistant media for critical information storage. The selection of appropriate metals and alloy compositions required understanding of chemical stability and corrosion resistance that enabled inscription preservation in hostile environments. Archaeological evidence demonstrates that bronze inscriptions remain readable after 3,000 years when properly formulated and protected. Ancient preservation systems often incorporated multiple complementary technologies that provided redundant protection against different degradation mechanisms. Important information was frequently recorded on multiple media and stored in different locations, creating preservation networks that ensured survival even when individual storage systems failed. This systematic approach to information preservation demonstrates understanding of risk management principles that parallel modern data backup strategies. The environmental control systems employed by ancient archives demonstrate sophisticated understanding of preservation chemistry and environmental factors. Ancient librarians developed storage techniques that controlled humidity, temperature, and atmospheric composition to optimize preservation conditions for organic materials. The Library of Alexandria and other ancient repositories employed systematic preservation methods that enabled document survival for centuries. Modern digital storage faces preservation challenges that ancient systems solved through material selection and environmental control. Contemporary magnetic and optical media degrade within decades, while solid-state storage systems face limitations from charge leakage and material degradation. The longevity achieved by ancient preservation systems suggests approaches to information storage that may inform development of long-term digital preservation technologies. Ancient communication networks. The transmission of information across vast distances challenged ancient civilizations to develop communication systems that enabled coordination of complex activities without electronic infrastructure. The solutions they developed demonstrate understanding of signal propagation, network topology, and information encoding that enabled effective long-distance communication across continents and civilizations. Greek fire beacon networks represented sophisticated optical communication systems that transmitted signals across distances exceeding 30 kilometers between mountaintop stations. The precision required for effective beacon communication demanded understanding of atmospheric optics, signal timing, and network coordination that enabled reliable message transmission across the mountainous terrain of ancient Greece. Archaeological evidence reveals beacon stations positioned with mathematical precision that optimized signal propagation while minimizing atmospheric interference. The Polybius telegraph system employed torch arrangements in grid patterns that enabled transmission of complex alphabetic messages rather than simple alert signals. This encoding system used 5 by 5 grids where torch positions represented specific letters, creating communication capability that rivaled early electrical telegraph systems in information capacity. The precision required for reliable torch telegraph operation demanded systematic training and standardized procedures that ensured consistent signal interpretation across the network. Roman heliograph systems used polished bronze mirrors to reflect sunlight across theoretical distances exceeding 130 miles through relay station networks. The optical precision required for effective heliograph communication suggests understanding of reflection geometry and atmospheric optics that enabled reliable signal transmission under optimal conditions. Military applications of mirror communication provided tactical advantages that influenced the outcomes of major campaigns. Chinese signal networks incorporated multimodal communication systems that combined visual signals, fire and smoke, with auditory signals, drums and horns, to create comprehensive communication capabilities. The integration of different signal types provided redundancy that ensured message transmission under varying environmental conditions while enabling complex information encoding through coordinated multi-channel signaling. The coordination required for effective ancient communication networks demonstrates organizational capabilities that parallel modern telecommunications management. Signal operators required systematic training in encoding procedures, timing protocols, and equipment maintenance that enabled reliable network operation across vast geographic areas. The precision achieved in ancient communication suggests systematic approaches to network design and operation that rival contemporary methods. Ancient communication networks achieved information transmission speeds that approached the theoretical limits imposed by signal propagation physics. Fire beacon signals could traverse hundreds of miles within hours, while coordinated relay systems enabled message transmission across continents within days. These achievements represent optimization of communication speed using available technology that demonstrates sophisticated understanding of network efficiency principles. The information legacy. The information storage and transmission systems of ancient civilizations reveal patterns of technological achievement that challenge conventional understanding of predigital capabilities. From the three-dimensional databases of Quipu systems to the undeciphered complexity of lost scripts, from preservation technologies that outlast modern media to communication networks that span continents, these achievements demonstrate systematic approaches to information management that parallel contemporary digital systems. The sophistication evident in ancient information technologies suggests not just individual innovation, but systematic knowledge transmission that enabled consistent development and refinement of complex encoding and preservation methods. The global distribution of comparable achievements implies either independent development of similar techniques or communication networks that transmitted complex information management knowledge across ancient civilizations. The loss of many ancient information technologies represents one of history's most significant intellectual tragedies. When traditional knowledge systems were disrupted by cultural change or technological displacement, the accumulated wisdom of millennia vanished within generations. The preservation challenges that defeated ancient systems continue to challenge modern digital storage, suggesting that lessons from ancient preservation methods may inform contemporary information management strategies. The study of ancient information systems reveals cognitive achievements that challenge our understanding of human intellectual capacity. The ability to develop and operate complex three-dimensional encoding systems, to create preservation technologies that function across millennia, and to coordinate communication networks spanning continents demonstrates mental capabilities that rival modern computational systems, achieved through systematic knowledge development that enabled extraordinary human performance. From these ancient archives where knowledge was preserved against the erosion of time itself, our investigation reaches its culmination in examining why these technological mysteries persist and what their existence reveals about the true extent of human achievement across the millennia. The Great Mystery. Why can't we explain them? From the ancient archives where civilizations encoded their deepest knowledge in three-dimensional matrices and preservation systems that outlasted empires, we arrive at perhaps the most profound question of our investigation. Why, despite all the sophisticated analytical tools of modern science, do these ancient achievements continue to baffle our understanding? If our ancestors possessed the foresight to create information systems that could transmit knowledge across millennia, why have so many of their most remarkable technologies vanished without trace, leaving only tantalizing artifacts that mock our attempts at comprehension? The persistence of these technological mysteries represents more than gaps in archaeological knowledge. It reveals fundamental challenges in how human knowledge is created, preserved, and transmitted across generations. The very information systems we have just examined, sophisticated as they were, ultimately failed in their most crucial mission, ensuring that the knowledge they encoded would survive the civilizations that created them. This failure illuminates a paradox that strikes at the heart of human technological development. Our greatest achievements are often our most fragile, dependent on knowledge systems so complex and integrated that they become vulnerable to catastrophic loss. The question of why modern science struggles to explain ancient achievements forces us to confront uncomfortable truths about the nature of knowledge itself. Despite our advanced instruments, computational models, and comprehensive theories, we find ourselves humbled by technologies that were created by people working with supposedly primitive tools and limited understanding. The answer lies not in the inadequacy of ancient peoples, but in the complex interplay of factors that determine how knowledge survives the passage of time and the fundamental differences between ancient and modern approaches to technological development. The fragility of knowledge transmission. The loss of ancient technologies begins with understanding the delicate mechanisms through which complex knowledge passes from one generation to the next. Unlike modern scientific knowledge, which exists in multiple forms, written theories, documented procedures, standardized measurements, and reproducible experiments, ancient technological knowledge often resided in the minds and hands of master craftsmen, whose skills were transmitted through apprenticeship systems that could be disrupted by a single generation of catastrophe. The Damascus steel mystery exemplifies this vulnerability perfectly. The technology that created the world's finest medieval blades depended on a complex intersection of specific sources, traditional smelting techniques, and generational craftsman knowledge that had been refined over centuries. When the ore deposits changed composition, traditional trade routes were disrupted, and master smiths died without passing on their complete knowledge. The entire technological system collapsed. Modern metallurgists can analyze the molecular structure of surviving blades with extraordinary precision, yet they cannot fully recreate the traditional process because the crucial knowledge was encoded not in written formulas but in the accumulated experience of craftsmen who are now centuries dead. The Roman concrete achievement reveals another dimension of knowledge transmission failure. The superior properties of Roman cement resulted from the integration of specific volcanic ash sources, traditional mixing techniques, and construction methods that were passed down through guild systems and practical training. When the Western Roman Empire collapsed and traditional construction guilds were disrupted, the knowledge vanished within a generation. Modern chemical analysis can identify the components and understand the reactions that create Roman concrete's self-healing properties. But recreating the complete traditional process requires understanding contextual factors, specific material sources, environmental conditions, and practical techniques that existed only in the memories of ancient practitioners. The Quipu information systems of the Inca Empire demonstrate perhaps the most tragic example of knowledge transmission failure. These sophisticated three-dimensional databases encoded the administrative complexity of an entire civilization in arrangements that modern computer scientists recognize as remarkably advanced information storage systems. Yet the knowledge required to interpret quipu died with the Quipucamayaks, who were systematically eliminated or suppressed during Spanish colonization. The physical quipu survive, their encoded information tantalizingly visible but largely inaccessible because the interpretive keys exist only in cultural memories that were deliberately destroyed. The vulnerability of ancient knowledge systems extended beyond individual techniques to encompass entire approaches to understanding and manipulating the natural world. Ancient civilizations often integrated practical knowledge with spiritual, mathematical, and astronomical understanding in ways that created powerful technological capabilities, but also made them vulnerable to cultural disruption. When belief systems changed, political orders collapsed, or foreign technologies displaced traditional methods, the integrated knowledge systems that had taken centuries to develop could vanish within decades. Material dependencies and environmental constraints. The mystery of ancient technological achievements deepens when we consider their dependence on specific materials, environmental conditions, and resource networks that no longer exist or have changed beyond recognition. Many ancient technologies were optimized for particular geological sources, climatic conditions, and ecological systems that have been altered by human activity, natural change, or simple exhaustion over the intervening millennia. The anti-corrosion properties of the Delhi iron pillar resulted from metallurgical techniques that deliberately incorporated phosphorus from specific wood types growing in particular ecological zones of ancient India. The traditional smelting process used Cassia auriculata and other phosphorus-rich plants that were selected through generations of experimentation to optimize iron properties. Modern attempts to recreate this technology face the challenge that the original ecological systems have been altered by deforestation, agriculture, and industrial development, making it difficult to source materials with identical chemical properties. The acoustic achievements of ancient architecture depended on precise combinations of local stone types, environmental conditions, and construction techniques that were optimized for specific geographic locations. The extraordinary acoustic properties of the Theatre of Epidaurus result from the unique properties of local limestone combined with atmospheric conditions and acoustic characteristics specific to that location. Modern attempts to recreate these effects in different environments consistently fail to achieve the same level of acoustic perfection because the technology was inherently site-specific. Ancient astronomical achievements often depended on environmental conditions that no longer exist. The precision of ancient star maps and astronomical calculations may have been enabled by atmospheric clarity and minimal light pollution that allowed naked-eye observations of extraordinary accuracy. Modern attempts to replicate ancient astronomical observations using traditional methods are compromised by environmental changes that make such precision impossible to achieve without technological aids. The global climate changes that have occurred since ancient times have altered the environmental conditions that many ancient technologies were designed to exploit. Ancient hydraulic systems, agricultural techniques, and construction methods were often optimized for specific climatic patterns that have shifted over the centuries, making it difficult for modern researchers to understand how these technologies functioned in their original contexts. The survivorship bias challenge. One of the most significant obstacles to understanding ancient technological capabilities lies in the selective nature of what survives for modern analysis. The artifacts and structures that remain after millennia represent only the most durable and exceptional examples of ancient work, creating a distorted impression of typical ancient capabilities that inflates our perception of their routine technological achievements. The precision stonework at sites like Puma Punku and Sacsayhuaman represents the highest quality ancient construction, preserved precisely because of its exceptional durability and precision. The thousands of more typical stone structures that were built with less precision have succumbed to weathering, earthquake damage, and human reuse over the centuries. Modern analysis of surviving megalithic structures therefore examines the very best ancient work rather than representative samples, creating the impression that extraordinary precision was routine rather than exceptional. Similarly, the metal artifacts that survive from ancient times often represent the finest examples of ancient metallurgy. Objects made from precious metals or exceptional alloys were more likely to be preserved, protected, and maintained across the centuries, while typical metalwork corroded, was recycled, or simply wore out through use. The Damascus steel blades in modern collections represent the finest examples of medieval metallurgy rather than typical weapons, contributing to inflated impressions of ancient metallurgical capabilities. The manuscripts and information storage systems that survived the destruction of ancient libraries and archives represent a tiny fraction of the original corpus of ancient knowledge. The documents that were copied, recopied, and carefully preserved across generations were often the most important or most durable texts, while routine technical manuals, practical guides, and everyday documentation were lost. Modern understanding of ancient knowledge systems is therefore based on exceptional preservation rather than representative sampling. This survivorship bias extends to our understanding of ancient practitioners themselves. The ancient craftsmen whose names and achievements are remembered in historical records were typically the most exceptional masters rather than typical workers. The technological capabilities we associate with ancient civilizations may therefore represent peak achievements rather than standard practice, creating misleading impressions of widespread technological sophistication. Modern analytical limitations. Despite the sophisticated instruments and comprehensive theories available to contemporary researchers, modern science faces fundamental limitations in understanding ancient achievements that go beyond simple technological inadequacy. The challenge lies not in the power of modern analytical tools, but in the assumptions and methodological approaches that guide their application to ancient artifacts and technologies. Modern reverse engineering typically assumes that understanding the composition and structure of ancient artifacts will reveal the methods used to create them. However, this approach often fails when applied to ancient technologies because it cannot recover the tacit knowledge, the subtle techniques learned through experience, that was crucial to ancient manufacturing processes. Spectroscopic analysis can identify every element in Damascus steel, but it cannot reveal the traditional smith's understanding of fire color, metal texture, and forging rhythm that was essential to the original process. The reductionist approach of modern science, which seeks to understand complex systems by analyzing their components, often misses the integrated nature of ancient technologies. Ancient achievements frequently resulted from the systematic integration of multiple disciplines: astronomy, mathematics, engineering, materials science, and practical craftsmanship, in ways that modern specialization makes difficult to replicate. Understanding the individual components of ancient technologies may be insufficient to recreate their complete functionality. Modern experimental archaeology faces limitations in recreating the full context of ancient technological development. Contemporary attempts to replicate ancient achievements often work within time constraints, budget limitations, and safety requirements that prevent the kind of extended experimentation and iterative refinement that characterized ancient technological development. The decades or centuries of gradual improvement that created ancient masterworks cannot be compressed into modern research timelines. The cultural context that surrounded ancient technological development cannot be fully reconstructed through archaeological evidence alone. Ancient technologies often operated within belief systems, social structures, and economic networks that influenced their development and application in ways that modern researchers can only partially understand. The loss of cultural context makes it difficult to comprehend the full significance and functionality of ancient technological achievements. The integration challenge. Perhaps the most significant obstacle to understanding ancient technologies lies in their integrated nature. Ancient civilizations often approached technological challenges through holistic methods that combined practical experience, theoretical understanding, and intuitive knowledge in ways that modern scientific compartmentalization struggles to match. The boundaries between disciplines that characterize modern science, physics, chemistry, engineering, mathematics, did not exist in ancient knowledge systems, enabling integrated approaches to problem-solving that modern specialization makes difficult to recreate. Ancient astronomical achievements demonstrate this integration challenge clearly. Maya astronomers were simultaneously mathematicians, engineers, architects, and religious practitioners whose astronomical calculations served multiple purposes within integrated cultural systems. Modern attempts to understand Maya astronomy often focus on individual aspects, mathematical accuracy, observational techniques, or architectural alignments, without fully grasping the integrated nature of the knowledge system that made these achievements possible. The precision manufacturing evident in ancient mechanical devices like the Antikythera mechanism required integration of metallurgy, mathematics, astronomy, and mechanical engineering in ways that transcended modern disciplinary boundaries. Ancient craftsmen who created these devices possessed knowledge that spanned multiple modern specializations, enabling them to optimize designs through approaches that modern engineering teams, despite their greater specialized knowledge, find difficult to match. Ancient chemical achievements often resulted from the integration of practical experience with theoretical understanding that modern chemistry, despite its sophisticated molecular models, cannot fully replicate. The pharmaceutical knowledge of ancient practitioners combined understanding of plant chemistry, human physiology, psychological factors, and preparation techniques in holistic approaches that modern medicine, with its emphasis on isolated active compounds, struggles to recreate completely. The temporal perspective problem. Modern science faces a fundamental challenge in understanding ancient technologies because it operates within temporal frameworks that differ drastically from ancient technological development. Contemporary research projects typically span years or decades, while ancient technological achievements often required centuries of gradual refinement and intergenerational knowledge transmission that cannot be replicated within modern institutional timescales. The precision achieved at megalithic sites like Stonehenge and Göbekli Tepe may have resulted from construction projects that spanned multiple generations, with knowledge and techniques being refined continuously over centuries of building activity. Modern attempts to understand these achievements typically examine them as completed products rather than as outcomes of extended developmental processes, missing the temporal dimension that was crucial to their creation. Ancient materials science achievements often involved multi-generational experimentation with local resources, environmental conditions, and processing techniques that enabled optimization through extended trial and refinement. The superior properties of ancient materials may have resulted from this extended temporal perspective that allowed for gradual improvement and adaptation that modern research, with its emphasis on rapid results, cannot replicate. The cultural knowledge systems that supported ancient technological achievement operated within temporal frameworks that encompassed multiple human lifespans. Master-apprentice relationships that transmitted complex technical knowledge often spanned decades, while the cultural institutions that supported technological development, guilds, religious orders, royal workshops, provided continuity across centuries. Modern institutional structures, with their emphasis on short-term results and individual achievement, cannot replicate these extended temporal knowledge systems. The persistence of mystery. The endurance of these ancient technological mysteries, despite the application of increasingly sophisticated analytical techniques, reveals fundamental aspects of how human knowledge operates across time. The persistence of these enigmas is not a failure of modern science, but a reflection of the complex nature of technological knowledge itself and the challenges inherent in recovering information that was never intended to survive the dissolution of the cultures that created it. Each mystery we have examined, from precision stone cutting to self-healing concrete, from astronomical computers to three-dimensional databases, represents the convergence of factors that are difficult or impossible to recreate. Specific material resources, traditional knowledge systems, skilled practitioners, environmental conditions, and cultural contexts that existed only briefly in human history. Their study continues to yield insights that inform modern technological development while serving as reminders of the remarkable diversity of approaches that human societies have developed for manipulating the physical world. The great mystery of why we cannot explain these ancient achievements ultimately reveals more about the nature of human knowledge than about the limitations of either ancient or modern capabilities. Knowledge is not simply information that can be stored and transmitted like data. It is a complex integration of understanding, skill, and cultural context that depends on human communities for its existence and transmission. From this sobering recognition of why these mysteries persist, our investigation reaches its final destination: understanding what these ancient achievements reveal about the true extent of human capability and their continuing influence on our contemporary world. Conclusion: what the ancients knew. From the sobering recognition that human knowledge transcends mere information storage, that it exists as a living, breathing synthesis of understanding, skill, and cultural memory, we arrive at the ultimate revelation of our investigation. The ancient technological mysteries we have explored are not simply puzzles waiting to be solved by more sophisticated analysis or better instruments. They are windows into forms of human capability that challenge our most fundamental assumptions about the relationship between technological development and historical progress, between scientific understanding and practical achievement, between individual genius and collective wisdom. The evidence we have assembled across 8 realms of ancient achievement, from impossible precision in stone cutting to molecular mastery in chemical preservation, From astronomical computers that predicted eclipses to navigation systems that mapped the Pacific Ocean, from self-healing materials to three-dimensional information storage, reveals a truth that transforms our understanding of human civilization itself. Our ancestors were not primitive people struggling toward modern enlightenment, but sophisticated practitioners of technologies that often exceeded contemporary capabilities through different pathways of knowledge development. The implications of this recognition ripple through every assumption we make about human progress, technological development, and the relationship between ancient and modern worlds. These discoveries force us to abandon linear models of advancement and embrace a more complex understanding of how human societies develop, lose, and rediscover technological capabilities across the vast expanse of time. The pattern of lost genius. As we step back from the individual mysteries to examine the broader pattern they reveal, we encounter evidence of human technological capability that operated according to principles fundamentally different from modern industrial development. Ancient achievements were not crude approximations of modern techniques, but alternative approaches to manipulating the physical world that often achieved superior results through methods that modern science is still struggling to understand. The precision stonework at sites like Pumapunku and Sacsayhuaman demonstrates manufacturing capabilities that rival modern CNC machining, achieved through techniques that left no trace in the archaeological record beyond the finished products themselves. The absence of the tools and methods that created these monuments suggests technological approaches so different from contemporary manufacturing that we lack conceptual frameworks for understanding them. These achievements force us to consider that precision manufacturing may be achievable through pathways that industrial civilization has not explored. The metallurgical mysteries we have examined reveal similar patterns of alternative technological development. Damascus steel achieved properties that modern materials science recognizes as incorporating nanotechnology, yet the traditional methods bore no resemblance to contemporary manufacturing processes. The Delhi iron pillar demonstrates corrosion resistance that exceeds modern weathering steel, created through techniques that integrated chemistry, metallurgy, and materials science in ways that transcended the disciplinary boundaries that characterize contemporary engineering. The astronomical achievements of ancient civilizations reveal computational capabilities that operated without mechanical aids yet achieved precision that rivals modern instruments. Maya astronomer-mathematicians predicted planetary movements with accuracy that wouldn't be matched until the computer age, while Polynesian navigators created mental GPS systems that enabled transoceanic voyages with precision that astonishes contemporary sailors. These achievements suggest that human cognitive capabilities, when properly trained and systematically applied, can exceed the performance of technological instruments in ways that challenge our understanding of the relationship between human intelligence and artificial computation. The chemical mastery evident in ancient preservation technologies, pharmaceutical formulations, and materials science demonstrates molecular manipulation that parallels modern laboratory techniques while operating through entirely different theoretical frameworks. Egyptian embalmers achieved tissue preservation that modern biochemistry struggles to replicate. Roman engineers created self-healing concrete that outperforms contemporary materials, and ancient chemists developed pigments and materials whose durability exceeds modern synthetic alternatives. Implications for understanding human civilization. The recognition that ancient civilizations possessed sophisticated technological capabilities that were subsequently lost forces us to reconsider fundamental assumptions about the nature of human progress and civilizational development. The evidence suggests that technological advancement is not necessarily cumulative or irreversible, that human societies can achieve remarkable capabilities and then lose them completely, requiring centuries or millennia for recovery. This pattern of technological loss and recovery appears throughout human history. The destruction of the Library of Alexandria represents more than the loss of individual texts. It exemplifies the vulnerability of entire knowledge systems to political upheaval, cultural change, and institutional failure. The collapse of Roman engineering capabilities during the medieval period demonstrates how technological knowledge can vanish when the social and economic systems that support it are disrupted. The loss of Damascus steel production illustrates how traditional technologies can disappear when resource networks, cultural practices, and craftsman communities are broken. The implications extend beyond individual technologies to encompass entire approaches to knowledge development and technological innovation. Ancient civilizations often integrated practical experience with theoretical understanding in ways that created powerful technological capabilities while making them vulnerable to systemic disruption. The holistic nature of ancient knowledge systems, where astronomy, mathematics, engineering, metallurgy, and craftsmanship were unified rather than compartmentalized, enabled achievements that transcended the capabilities of individual disciplines while creating dependencies that made the entire system fragile. Modern industrial civilization operates according to different principles that emphasize standardization, documentation, and systematic knowledge preservation. Contemporary technologies are designed to be reproducible, scalable, and independent of individual expertise in ways that provide greater resilience against knowledge loss. However, this approach may also limit the kinds of technological achievements that are possible, creating trade-offs between systemic stability and peak performance that ancient civilizations resolved differently. The study of ancient technological mysteries suggests that human societies have consistently developed capabilities that exceeded the apparent limitations of their tools and theoretical understanding. This pattern implies that technological potential is not strictly determined by available materials or formal scientific knowledge, but depends on factors such as cultural priorities, knowledge transmission systems, and approaches to integrating different forms of understanding. Modern rediscovery and technological renaissance. The investigation of ancient technologies is not merely an academic exercise. It represents a form of technological archaeology that continues to yield insights with immediate practical applications. The rediscovery of Roman concrete principles has already begun to transform modern construction practices, while the study of ancient materials science informs contemporary research in biomimetic materials, sustainable chemistry, and precision manufacturing. The breakthrough understanding of Roman concrete's self-healing properties, achieved through MIT and Harvard research in 2023, exemplifies how ancient wisdom can solve contemporary problems that modern technology created but cannot address. The concrete industry's massive carbon footprint and the short lifespan of modern concrete structures represent challenges that Roman techniques can help solve. Companies are now developing Roman-inspired concrete formulations that could dramatically reduce construction's environmental impact while creating infrastructure that lasts millennia rather than decades. The study of ancient astronomical instruments like the Antikythera mechanism has influenced modern research in mechanical computation, precision manufacturing, and analog computing systems. The device's sophisticated gear ratios and computational capabilities demonstrate principles that inform contemporary work in mechanical engineering and computational design. NASA researchers have studied ancient astronomical knowledge to understand long-term celestial mechanics and develop more accurate models for space navigation. Ancient navigation techniques continue to influence modern research in human-computer interaction, cognitive science, and navigation technology. The study of Polynesian wayfinding has revealed human cognitive capabilities that inform research in spatial cognition, environmental perception, and navigation system design. Military and civilian navigation researchers study traditional techniques to develop backup systems that can function when electronic infrastructure fails. The pharmaceutical knowledge embedded in ancient medical systems continues to provide sources for modern drug development. Traditional Chinese medicine processing techniques that deliberately modify molecular structures to enhance therapeutic effectiveness have informed contemporary pharmaceutical research in drug formulation and delivery systems. Ancient anesthetic protocols provide insights into multi-drug approaches to pain management that complement modern anesthetic practice. The future of ancient wisdom. As our analytical capabilities continue to advance, the investigation of ancient technologies reveals new layers of sophistication that suggest we have only begun to understand the full extent of ancient achievements. Artificial intelligence and machine learning are being applied to decipher ancient scripts, analyze construction techniques, and model technological processes in ways that may unlock secrets that have remained hidden for millennia. Recent applications of AI to archaeological research have already yielded remarkable results. Machine learning algorithms have identified previously unknown astronomical alignments in ancient monuments, revealed hidden patterns in undeciphered scripts, and modeled construction techniques that explain how massive stone monuments were created with primitive tools. These computational approaches may finally provide the analytical power necessary to unlock the most persistent ancient mysteries. The development of increasingly sophisticated materials analysis techniques continues to reveal new aspects of ancient technological achievement. Nanoscale analysis of ancient materials has uncovered evidence of deliberately engineered structures that approach modern nanotechnology, while advanced chemical analysis has revealed processing techniques that parallel contemporary materials science. As our analytical resolution improves, we continue to discover that ancient achievements were more sophisticated than previously understood. Virtual reality and digital reconstruction technologies enable researchers to model ancient technologies in ways that were previously impossible. Complete virtual reconstructions of ancient workshops, construction sites, and manufacturing processes allow researchers to test theories about ancient techniques and explore technological possibilities that the physical evidence alone cannot reveal. These digital approaches may enable recovery of ancient knowledge that existed only in the memories and skills of long-dead practitioners. The integration of multiple research disciplines, archaeology, materials science, computer science, cognitive psychology, and engineering, creates opportunities for understanding ancient technologies that no single field could achieve alone. Interdisciplinary research teams are developing new approaches to technological archaeology that combine traditional archaeological methods with cutting-edge analytical techniques in ways that reveal previously hidden aspects of ancient achievement. Lessons for contemporary civilization. The study of ancient technological mysteries offers profound lessons for contemporary civilization about the nature of knowledge, the relationship between technology and society, and the factors that determine whether human achievements survive across generations. These lessons become increasingly relevant as modern society faces challenges of sustainability, technological dependence, and knowledge preservation in an era of rapid change. The fragility of ancient knowledge systems serves as a warning about the vulnerability of contemporary technological civilization. Despite our sophisticated documentation systems and global communication networks, modern society remains dependent on complex technological infrastructures that could be disrupted by natural disasters, social upheaval, or systematic failure. The study of how ancient civilizations lost technological capabilities provides insights into the factors that threaten knowledge preservation and technological continuity. The holistic approaches that characterized ancient technological development offer alternatives to the specialized, compartmentalized methods that dominate contemporary innovation. Ancient achievements often resulted from integration across multiple disciplines in ways that modern institutional structures make difficult to replicate. Understanding how ancient knowledge systems achieved this integration may inform efforts to address contemporary challenges that require interdisciplinary approaches. The sustainability principles embedded in many ancient technologies provide models for developing contemporary alternatives to resource-intensive industrial processes. Ancient materials science achieved remarkable results using locally available resources and renewable energy sources in ways that modern industry, with its dependence on global supply chains and fossil fuel energy, might learn from. The temporal perspectives that guided ancient technological development challenge the short-term thinking that characterizes much contemporary innovation. Ancient achievements often required multi-generational planning and execution that created results of extraordinary durability and sophistication. Understanding how ancient societies maintained long-term technological projects may inform efforts to address contemporary challenges that require sustained commitment across multiple human generations. The eternal questions. As our investigation concludes, we must acknowledge that some ancient mysteries may remain forever beyond our comprehension. The knowledge systems that created these remarkable achievements were products of their time, embedded in cultural contexts and practical traditions that cannot be fully reconstructed through archaeological evidence alone. The loss of crucial knowledge, the tacit understanding that existed only in the minds and hands of ancient practitioners, means that some ancient technologies may represent permanent mysteries that serve as reminders of human capabilities that once existed but can never be fully recovered. Yet the persistence of these mysteries serves a crucial function in maintaining human humility before the vastness of what we do not know. In an age when technological confidence sometimes exceeds technological wisdom, ancient achievements remind us that human potential has consistently exceeded expectations and that the boundaries between possible and impossible are far more fluid than we imagine. The ancient mysteries we have explored challenge us to expand our conception of human capability while recognizing the complex factors that determine whether achievements survive across the generations. They demonstrate that technological sophistication can be achieved through multiple pathways, and that modern approaches to manipulating the physical world represent only one possible solution to the challenges that all human societies face. Perhaps most importantly, these ancient achievements remind us that the story of human technological development is far from complete. If our ancestors could achieve such remarkable results with tools and techniques that seem primitive by contemporary standards, what might be possible through approaches that we have not yet imagined? The mysteries of the past may point toward possibilities for the future that our current technological paradigms prevent us from seeing. The ancient world speaks to us across the millennia through monuments and artifacts that continue to challenge our understanding and inspire our imagination. Their achievements remind us that human genius has always found ways to transcend apparent limitations, creating technologies that serve as permanent testaments to the remarkable capabilities that emerge when human intelligence, creativity, and determination are applied to understanding and manipulating the physical world. In the end, the greatest mystery may not be how ancient civilizations achieved these remarkable technologies, but how human beings, then as now, continue to push beyond the boundaries of what seems possible, creating achievements that inspire wonder and challenge understanding across the vast expanse of time itself. The story of human technological achievement is not a linear progression from primitive to sophisticated, but a complex tapestry of capabilities gained, lost, and rediscovered that reminds us that the future of human achievement remains as unlimited as the human imagination itself.